Okay, hello everyone. Welcome to day 2 of our workshop. Welcome to everyone here and at home. We are going to get started in a minute with our first speaker, András Halász. Yes, I can hear myself.
Okay, so hello everyone, I'm Halász András and my presentation will be about the preliminary results of an open set recognition algorithm. First, what exactly is the open set recognition? With which one can I step it? All right, so in the classical closed-set classification scenario, we have the promise that every sample which can occur during the use of the model belongs to a class which we know during the training. And so it is a good solution to assign the label of the most probable class. So, for example, we can separate in the feature space with the hyperplanes, and on the current side of the hyperplanes, we assign everything to that class. So there are data sets on which this classification is almost perfect. For example, on the MNIST, the current precision is about 99 point a lot, so closer to 100. And this practically cannot be further improved because at such a level of accuracy if the model says it's an 8 and the label is a 9, so who is right? For example, in high school, my teachers often misclassified my handwritten digits also. So, but the situation is completely different in that more real case when unknown samples can occur. So, for example, we classify, train a model to classify cats and dogs, and then we give him a bear. And in the former case, it will classify as either one, and probably with very high confidence. Of course, we cannot expect our model to classify this new sample as a bear because it, of course, never seen any. But we can expect it to reject it, saying that I don't know what it is, I've never seen anything like this before. So partitioning in the feature space is not a good solution. Therefore, for example, those question marks, you don't see my cursor, right? All right, so the question marks on the right, upper right corner is clearly a new class, but if we separate with hyperplanes, those will be classified as these red diamonds with very confidently. So what can we do? My approach to solve this problem is a distance-based model. I want to transform the samples to a different feature space, and we want in that feature space that the samples which belongs to the same class to be close to each other, and samples from another different classes to be far from each other. So the training will basically that the same class samples will attract each other, and the different class samples will repel each other. If we manage to do this, what will we gain from it? We start with this situation where the samples are really messed up and overlapping. All right, this might be maybe a bit extreme example. This maybe cannot be separated, but assume we can do it. So when we do this, then the same class samples will form such a small blobs, because they attract each other and will occupy a small space. But because the samples from different classes repel each other, these small blobs will be far from each other. So in conclusion, they will span a relatively big space, but the samples will occupy only a small part of it. So most of this span space will be void. And if we assume that the unknown samples are really far from any known classes, then we can also assume that these will land randomly on the feature space. So with very high probability, these will land on the void, far from every known samples, and which is more important, far enough to distinguish them from all of this. So I will implement. I implemented this only partly with a neural network. I use first a common feature extractor, which is good for the current data set. So, for example, on images, a convolutional network is good, but we don't need the final softmax layer, because that will lead to the classical closer classification. But instead, I add some fully connected layers to it. It's not sure that it is really necessary, or it works fine without this, only with cutting down the softmax layer. This will need further experiments. So the training will happen the following way. We divide the samples into batches, and of course we shuffle the batches in each iteration, so the order will be random, and run all the samples in the batches through the network. and calculate the pairwise distance in this batch. And then for every distance instance, we calculate the loss function, which is the square of the distance in the case of same class samples, and in the case of the different class samples, it will be the square of the difference between a specified constant and the actual distance. Actually, our model is completely independent of the choice of this constant, because if we choose a constant half of the original and we divide all the weights and biases by 2 in the final layer, then we get exactly the same model, only scaled down by 2. So after we train our model this way, we calculate the average feature vector from each class, and our model will then consist the class means, the neural network, and some threshold in which when the distance from a class mean is below a threshold, we accept this sample belonging to this class. So we do not accept automatically the class with the nearest class mean from this sample, but we also check the the value of this distance. And this one is not implemented yet, so the result I can show you is a histogram of the distances. The green one is the same class samples, which should be small. The red is the different class samples, and the yellow is the most interesting, the open set images. So those images which we didn't see during training, or we didn't see anything, any of these, but we didn't see anything belonging to that class in the case of the yellows. So it's hard to see from hard to see the accuracy from this histogram, but I have calculated. The closest accuracy is 19%, so 10% of the other classes were misclassified, and each class rejected 98% of the open set, the unknown samples. I must say that it is for every class, so every class accepted 2%. So if we assume that these were not overlapping, then the actual error rate is the sum of these. So I trained on 6 classes, and there were 4 unknown classes. This was the CIFAR-10 data set. So if we take the worst case that these errors do not overlap, then 88% of all open set samples were rejected. But it is worth to note that the main peak, the green peak, is not anywhere around 0. So all of the same class samples are a bit far away from the class mean, and there are no samples right at the class mean. So how is it possible? I have analyzed the outputs with PCA and plotted it. The class mean is with the small red dot, maybe too small. And the blue ones are the actual outputs. So we can see that the vast majority of these outputs are on that bottom left corner, and on that big blob. But there are samples. Also on different places, and these also tend to form some blobs, so but smaller ones. So how can we solve this issue? The first one is we can use multiple centroids. So instead of calculating the class mean, we can calculate multiple class means, subclass means. But this is, of course, not an easy problem, because we have to decide whether a sample belongs to which of these subclass. It can be solved with a clustering method, but we don't know either. We don't know how many clusters we need. So after this clustering, we can even train our model further on the subclasses, and the training will be modified that only the samples belonging to the same subclass will attract each other. The samples with in different classes will repel each other, and the samples in same class but different subclass will either not doing anything with each other or attract each other, but with a lot smaller weight. Or we can use other statistical methods, the extreme probability theory, which Walter had spoke about yesterday. And of course, as I saw, the decision making is not implemented yet. So I only got histograms, but from those histograms, it is clearly visible that it is promising. So I summarized what happened. I've implemented partly a new method. Some of its parts are yet to be implemented, but the results are promising, and the way of continuing is clearly visible. So thank you for your attention. And feel free to ask any question, of course.
Thank you. Do let us know if anyone online has questions. You can raise your hand or just start talking if you're in the panel. Guys, locally, if anyone has a question. In the meanwhile, I do have one. Why do we mind that samples are a bit farther from the mean? Why is that the problem?
The main problem isn't that, but it warns us because it meant that there are other samples very far from away. So these.
Yeah,
All right, so the smaller blobs on the right, upper right or bottom right corner, not only move the class mean to further away from the bigger blob, but they still lies very far away from it. So those will be surely misclassified. So this is a really big distance, so our model will clearly reject them. Or if we make it so to accept them, then we will accept everything in this radius, which is very dangerous because there is a big chance that an unknown sample will land there.
So basically, they really should be a different class for classification purposes, which then may have the same label. But so in terms of model size, do you think so? You know, with CIFAR, I'm sure, and particularly with more complex problems, having these huge models with billions of parameters usually slightly improves accuracy. Does that have an effect in open set recognition? Does it help or does it raise problems?
Model complexity will be basically the same as in the closed set classifiers because the difference is not so huge, so a few more layers. And a bigger model, I don't know, it might help, but I think there's the same trade-off as in the closed set classification. So maybe the danger of overfitting or so.
So usually you would use or models with similar structure for closed set and open set.
Yeah, that's a good first step, and of course I will experiment on modifying this. So yes, it's possible that for open set recognition we need a slightly bigger or slightly smaller model, but I don't think this is probable. So
I'm raising my hand, you can see. Actually, I just want to add a comment. So if you remember yesterday Walter told us, yesterday Walter showed us a picture about the tails of the probabilities, and you could remember that these tails could overlap. And basically the intuition behind this work is that somehow minimize these overlapping tails, or have a transformation transformation helps us to separate better the different sets. And actually there could be problems where unknown images, you might remember also the unknown. If the unknown unknowns are considered as known classes, might cause real troubles, and we would like to avoid even we have the price, and that price is that we reject in some cases real class items. I think, or I guess that might give some enlightenments.
So I would like to ask, for this specific example, do I understand correctly that this is, so basically this is one class, but it's distributed in a weird way? And if so, then what kind of clustering would you suggest for separating the subclasses of this one? Because it really seems, this seems like a hard problem. Yeah, very good question, because it's exactly the issue we are currently working on. So I've tried out tons of clustering methods. So the most simple ones, the k-means, for example, works good in this if I know that there is 3 subclasses, as on this picture it is somewhat visible. But so far I haven't found such a clustering algorithm which is required to get the number of clusters as parameter and can this kind of structure cluster well. So it's not an easy issue, indeed.
My question, I think you answered. My question, I think you answered it already. You are using a feature-based, right? Not a featureless based for classification, right?
Sorry.
Feature. You are using a feature-based classifier. You are like extracting some features and work with it, right? What about using a featureless or unsupervised algorithm that extracts the feature itself and then try to classify based on this? Identify the features. That's what I'm asking.
Yes, so you mean some kind of descriptors or because I think my literature research showed me that those kind of feature extractors where we have to train, so convolutional network are much more efficient. So nowadays the state-of-the-art feature extractors are not these like SIFT or I think so. This one I used here, the VGGNet or the residual network, are far better today. A couple of years ago, these were the state-of-the-art, the SIFT or
Okay, if there are no further questions, then we are going to, I need to rearrange the screen a little bit here, but our next speaker is going to be Zsolt Márkos. Let me promote him. Zsolt, you should, yeah.
Okay, so you can see my slides and hear me.
You are very quiet, Zsolt. Please try and.
Okay, I will try to speak a bit more louder.
You should speak far more louder.
Okay, so good morning, everyone. I'm Márkos Zsolt, and I'm going to speak about the application of the long short-term memory networks in the forecast-based classification scheme on smart grids. I will start my presentation with shortly introducing the topic, the forecast-based classification method and the dataset. Then I will discuss the results, and finally I will draw a conclusion and mention the future plans. So the rise of green energy sources and the spread of smart and IoT technologies has led to a need for re-engineering the traditional electric grids. On this figure, we can see a comparison of the main features of a traditional on the left and a smart grid on the right. Among other aspects, smart grids are meant to be more distributed, allow two-way power flow, that is that consumers can participate with their photovoltaic panels or wind turbines, and are more efficient in resource management, as the storage of electrical energy in large amounts is quite expensive. Now, a requirement for proper resource management, it is to profile the consumers based on their consumption patterns. This may be attained by the analysis of the waste amounts of information recorded as energy consumption time series generated by the smart sensor networks the smart homes are equipped with. And we can see this process on this flow chart. Now the question is, how can we perform the classification of the consumers based on the consumption time series? Well, there are multiple methods for this. In my work, I have investigated the forecast-based classification method, the FBC, that based on previous results may be one of the most efficient approaches. The FBC scheme basically creates a grid of forecasters. So if you have n classes, then it trains n pieces of forecasters per class. And thus the dimension of this grid is going to be of n times m. What I mean here is that the parameters of a specific forecasting algorithm are tuned in the training phase by just those time series that belong to that specific class the forecaster is designed to represent. And the assumption of this full classification scheme is that the forecasters that represent a specific class can predict with low error rate any other measurement belonging to that same specific class, whereas the prediction of a measurement that belongs to another class results in a significantly higher error. So the classification itself is based on the comparison of the error rates. More specifically, arbitrary time series is classified into that class, which is represented by that forecasting algorithm that managed to predict it with the least error. And from here, we can see that an advantage of this classification scheme compared to other methods is that its performance does not directly depend on the statistical features of the measurements, but rather on the selected forecasting algorithm's performance. And I think that is some sort of transformation of the original classification problem into a regression problem. Now, let me briefly introduce the data set that has been used for testing. It contains 1 year-long hourly energy consumption measurements from the United States, and it was made available by the OpenAI. The original data set contains 16 classes. However, 2 subsets of this has been created, one containing 6 classes and another with 12 classes. This figure illustrates how this consumption time series do literally look like in the case of a restaurant and in the case of the hospital. And now let's talk about the forecasting algorithms themselves. I have used 2 different neural network structures as forecasters. Firstly, the nonlinear autoregressive or NAR networks are basically some very simple feed-forward neural networks. This figure illustrates one of them implemented in MATLAB. It has just 1 single hidden layer, and it has 24 hidden neurons in it, and that's it. Secondly, the long short-term memory networks, or LSTMs, are more sophisticated recurrent neural network structure, and I've used an implementation of them in PyTorch. And let's talk about the results. Firstly, those that have been achieved by the NAR networks. Well, these are more like previous results, and this presentation is about LSTMs, so I won't go into much details in here, but very briefly, after a through hyperparameter optimization, they managed to achieve around 90–92%, which is in fact a quite good result. And I wanted to introduce here a very interesting yet very logical feature of this consumption time series, and that is seasonality. It basically boils down to the fact that different seasons have a significant impact on energy consumption. Example, in winter, there is more energy consumed for heating and lighting. Now, because of this, the time series that belong to the same class, yet are from different seasons, are quite different. And that's the classification scheme that was trained by time series from a specific season may have a worse performance when tested on time series belonging to another season. This table illustrates how this cross-season evaluation influences the performance. As one can see from the table in, and yeah, it is not very surprisingly, the highest deviation is in the case of the pair of summer and winter. You can see here and here. And the least deviation is in the case of the pair of spring and fall. So why this feature is important? This is because for a proper performance analysis, one should measure the performance on the same season data. And yeah, finally, we have arrived to the LSTM networks. I've tried to perform with them hyperparameter optimization according to different aspects. Firstly, I've tried to find what may be the ideal length of the of the sliding window, or also known as the sequence length, that we input into the network. And in this table, you can see that the different performance is obtained by using sliding windows of different length from 4 hours to 24 hours. And there is one more parameter to introduce, the smoothing, which basically refers to if we have applied smoothing during the preprocessing or not. Well, smoothing was originally introduced in order to help the neural networks to process these raw consumption measurements that in most of the cases contain sharp edges. But as you can see from the table, the performance is usually lower with them. So in the future, maybe I should try out to decrease the weights of the neighbors, as currently I'm using a 4 hours wide Gaussian function for smoothing. And now back to the sequence length. As you can see from the table, the ideal length may be somewhere between 12 and 24 hours. And this may be attributed to the fact that most of the consumption time series exhibit some sort of periodicity over 24 hours, with some exceptions among the weekdays and weekends. Another aspect considering during the hyperparam optimization was whether to use uni or bidirectional LSTM network structures. And the results have shown, as you can see in this table as well, that it is beneficial to use bidirectional LSTMs over unidirectional ones, as they usually provide a performance gain of up to 4 or 5%. This finding may be attributed to that, similarly in NLP, the next values in this consumption time series do not only depend on the previous values, but rather on the whole context. Okay, yet another aspect to consider may be the minimal network structure. Why this would be feasible? Well, in the introduction, we have seen that these smart grids are meant to have a distributed structure. So we might want to solve this whole classification task on a small smart device that has a limited computation and energy resources. Some of the parameters that directly affect the size of the network are the number and size of the hidden layers. In addition to this, there are some parameters that indirectly add some complexity to the task by increasing the time needed for either the training or the evaluation. These are the sequence length that I have previously covered, and the length of the training and testing time series. Now, as we can see from the table, not very surprisingly, again, we can achieve better results by increasing the complexity. So what we really need to do is to leverage this trade-off between complexity and cost. For example, if we add an additional hidden layer, we can achieve slightly better results. However, the added complexity isn't really justified by the performance gain. In the case of the hidden size, we can see that it may be beneficial to set it to 168 hours or something like that, as there is more significant performance gain, up to 4% in this case. And finally, it may be also beneficial to increase the training, the length of the training time series used for training as much as we can. As you can see by this one we can achieve performances higher than 90%. However, if we want to stick to minimal complexity, an ideal setting would be of 720 hours, which is actually a month due to the periodical features of the consumption time series. So to conclude, we have seen that the task of classifying this consumption time series can indeed be solved by this forecast-based classification scheme with a really good performance. I have presented some previous performance results on using neural networks as forecasting algorithm in this classification scheme, as well as the seasonality feature of the dataset. Then I've introduced some results and ideas regarding that what we can do in a hyperparameter optimization if we want to use LSTM networks as forecasters. This included investigating the ideal length of the sliding window, the usage of bidirectional LSTM networks, and leveraging the minimal network structure. Now, in conclusion, we can see that LSTMs are a lot more complex than neural networks, and neural networks still perform almost this identically good. In the future, I would like to test these networks on a different data set, also consumption-based. So where maybe the neural networks, as they are simpler, do perform worse than the LSTMs that are considered to be more complex and more sophisticated. And I would also like to do in the future some further hyperparameter optimization of these networks to achieve better performances. And basically that was it. And thank you for your attention. And I'm happy to answer your questions.
Thank you, Zsolt. Questions, anyone? If you have one, please come walk up or ask online. So in the meanwhile, I have one. Have you tried looking in the spectral domain with FFTs or something?
Actually, I haven't tried that. I was mostly using, mostly dealing with the raw data. As you've seen, I have worked with not feature-based forecasting methods.
How much data do you have again?
Well, I have 1 year long hourly data, and for each class, I think I have like 900 and something like that. Pieces of time series.
Right. So do you expect to get maybe more so you can try networks with more complexity or parameters, or that's, you know, it's limited and then you're gonna have to move to some other input problem?
Yeah, that might be a good idea. I have to, as I have said, I have to try another data set that has maybe more time series per class.
If I would add a comment, the beauty of the data set is that in some cases the different classes are containing very same time series. I mean, the statistical properties, the values are basically indistinguishable. So this database also contains some interesting things inside.
Okay, we have another question here.
Not a question, just a comment. If you can also include another country, don't use the same country for example, or another region, because, for example, if you are talking about like a hot region and you are comparing this with a country like mine, Egypt, for example, you will get, for example, that we don't use that much heat in winter or something like this, compared to different countries like, I don't know, Hungary. For example, in here, it's very cold in winter that you need to use that much electricity or on the grid. Just a comment from me. That's all.
Yeah, that's a nice comment. Thank you. Yes, there are other countries with exhibit other seasonal features. I think the United States is very fortunate from this point of view because there are multiple regions within, for example, in Florida and the winter in New York. So we have a quite good coverage with that, but yeah, it might be a nice idea to try other data sets from Asia if they are available as well.
So do you actually have that information in the training set?
Which kind of information?
So what state the measurement is from, for example?
Yes, the training set is labeled with the region within the United States from where it is.
Oh, okay.
Oh, you can see here the link to the to the data set. Actually, it's the first reference.
Okay, any other questions? Okay, well then, thank you, Zsolt. Next up, we are going to move on to Tamás Kozsik from ELTE, who is going to tell us about our computers helping us write HPC code. I've promoted you to co-host, so you should be able to share your screen. Okay, you can see the screen. Also unmute yourself.
Hi, everyone.
Hello, all good to go? We can see you, hear you.
Okay, very good. Okay, so first of all, let me express my gratitude to the organizers of this wonderful event. And I'm going to present work with lots of researchers involved in the preparation of. Actually, it's 3 persons mentioned here on this slide: Daniel Horpácsi, Tamás Kozsik, and Melinda Todd, but lots of other researchers contributed. And of course, some parts of the research presented here was supported by the project, which also made this conference possible. So what am I going to talk about? I would like to investigate how refactoring helps us to introduce parallelism into sequential code. And my main question is that, can we provide trustworthy refactorings? So can we write refactorings in which all the users really trust that it works perfectly? So in the course of addressing this topic, we will see domain-specific language for pattern-based parallelism, and also we have a short discussion about domain-specific language for refactoring. The main question, well, still left unanswered by the end of the talk, is trustworthiness of these refactorings. So this is really ongoing work. So first, I will talk about refactorings in general. Then I will address a specific model of parallelism, a pattern-based approach, and show you examples of this domain-specific language. Related to a programming language called Erlang. I don't know how many of you have ever used Erlang before, but since my examples are related to this language, well, you will have some knowledge on Erlang by the end of this talk. Then I will present how we can refactor Erlang programs to the pattern DSL. And finally, we will talk about how to define DSL, which are able to describe refactoring transformations, and how we can develop trustworthy refactorings. So first, I start with refactoring. Probably many of you already know this concept. Refactoring means that we want to restructure our code without changing how it behaves, without changing its semantics. Why would we do that? Well, the number one reason is maintainability, of course. We would like to mitigate software erosion that I think is quite natural for every software to get old and old, and they, after a while, they will contain not really nicely written parts. They contain hack solutions, and after a while you want to remove them. So you would like to restructure the code a bit, reshape the code a little bit. That's very useful for maintainability point of view. But sometimes you want to do refactoring because you want to extend your functionality in the code. So you want to introduce new code into the code base, and before you can do that, you have to restructure what you have up to that point. So this is kind of paying back the technical debt. And finally, sometimes we do refactoring because we want to improve the performance of the code. So we have realized that the solution applied is not really good, it's not really efficient. So so we change the code a little bit, not actually what it does. So the code will compute whatever it computed before, but it computes a bit more efficiently. And what we are going to do today here is that we want to introduce parallelism into sequential code. So this clearly belongs to the third category. Doing refactoring manually is quite tedious, and it's quite error prone. So we really welcome any tools that offer automated transformations. Typically, these transformations are really very small steps, and the human, a programmer, guides through the tool. So the main decisions are made by the programmer, but all the cumbersome details are carried out by the tool. So this makes refactoring faster, of course, much easier, and hopefully more reliable. If you have well-written refactorings, then this whole process is going to be more reliable. The main point here is that we have to preserve the semantics of the code by changing the code. And this is extremely true if it is a tool which performs the refactoring. So if the tool is written properly, then it will create modifications on the code, which really does not change the meaning of the code. And the modifications are performed globally, so respecting the dependencies of the code parts. So you can avoid those errors which are related to manual refactoring, like copy and paste errors or replace all errors. Of course, this comes at a price, because if you do refactoring with a refactoring tool, then you have a limited expressiveness. You can only do what the tool is able to do. Whenever you encounter a problem that the tool cannot solve, you have to go back to manual refactoring, of course. There are many refactoring tools already available for you. Most of them are built in standard software development environments like Eclipse, IntelliJ, Visual Studio, Xcode. But there are many other tools which are either add-ons or plugins to these IDEs, or or completely standalone tools. These refactoring tools support a fairly well-known set of micro-refactorings. There is a catalog of object-oriented micro-refactorings by Martin Fowler, and many of these tools implement exactly those or very similar refactorings. They are very easy to use because you just need to click a few and then you can preview the changes, and if everything looks like you expected, you can apply the transformations. In spite of these nice features, there are still problems with the programmers' acceptance of such tools. So programmers believe that the tools might do something wrong to their code. Of course, they are also aware of the fact that they also make problems to their own code, so they can also mess up their own code base, but they probably believe that the way they mess up the code is less harmful than the way a tool messes it up. So that's still a problem. So what we have to do is to develop trust in programmers in the correctness of refactoring tools. Let me give you a few examples of typical micro refactorings. Renaming and moving definitions around. Reorder parameters of a function. Extract a function to make a big function into two small functions. Or the other way around, inline a function to merge the definition of two functions into one definition. The same for other entities like variables and classes. You can extract superclasses to create an abstract superclass from many classes. You can move members, fields, and methods between classes, pushing down the methods or members or pulling up in the inheritance tree. And there are more sophisticated micro-refactorings like replacing a constructor with a builder pattern or factory pattern. But these are sometimes language dependent, sometimes paradigm dependent refactorings, but most of the cases we can talk about these micro refactorings in any language, in any paradigm. How do you define a refactoring, by the way? Well, there are typically site conditions that you have to check before applying refactoring. If those site conditions do not hold, of course, you are not allowed to perform the refactoring because that would change the meaning of the program. If the site conditions hold, you can apply the transformation, which might perform modifications to the code at many places. So it's typically a global activity on the code base. The simpler case is when you don't have to change many compilation units, just change a single function. But these refactoring transformations are not that interesting. The really interesting ones are those that have consequences in the whole code base. Sometimes after performing the refactoring, you have to do some compensation to clean up the code after the changes. And of course, there is some interactive parameterization possibility in many of these refactorings. And the programmer can set, for instance, the name of a new function, or they can just rely on some default values. That's also very widespread. Okay, so that's all about refactoring, and now let's go to pattern-based parallelism. I think the motivation is very similar to all of us. We all know that writing parallel code is really, really hard, and even if we have a good idea what will happen in practice, it will not happen. So something else will happen, and to make parallelism work as in theory, you have to use really high-level tools in the programming language. So one approach to solve this problem is pattern-based parallelism. So we try to express parallel computations according to some well-known parallel patterns like task farms and pipelines and divide and conquer. And this way we can have a structured description of how parallel computation takes place in our code. So this is what we are going to follow in the rest of the talk. A few years ago, we took part in a very nice project, the Paraphrase project, which was coordinated by the University of St. Andrews, by Karen Hammond personally. And with many cool partners, we investigated how to facilitate the development of parallel code for heterogeneous hardware. And one of the key issues was here refactoring. So how we can support the introduction of patterns into code using refactoring. So this motivates my talk. We had two more or less distinct tool chains in Paraphrase, one dealing with C++ and another one dealing with Erlang. We have chosen two very different languages to see how the ideas carry over from one language environment to the other. So the C++ branch was developed by the Italian partners. Probably you have heard about FastFlow. This is a quite popular pattern-based parallel library, and it provides some very generic building blocks like nodes, combiners, farms, pipelines, all-to-all and feedbacks. And the top of these building blocks, you can design even more high-level patterns. Very similarly, we used a streaming parallel skeleton library for Erlang, which was developed by colleagues in Scotland. So these skeletons are composable using, well, actually an embedded domain-specific language. So this is how you use this DSL to describe a pipeline where the pipeline has two stages, and both stages are implemented by task farms. And inside a task farm, we have sequential components running. So in the first task farm, we have a sequential component which runs the read image function in 16 workers. And in the second stage of the pipeline, we have a task farm, again with 16 workers, which execute the convert merge function. So this is how you can use actually the data structures of the host language, the Erlang language, to describe the parallel computation scheme, the parallel pattern in this domain-specific language. Scala also has a hybrid skeleton facility, so you can use this this DSL to program heterogeneous multi-core machines. And well, there is an OpenSBLI binding for Erlang, and this is what is used by Lapido. The kernels have to be written in C by the programmer, and Lapido does all the automatic wrapper code generation, which is necessary to get it running in your Erlang machine. So what is Erlang? That's a very strange but really nice functional programming language. For those who are interested, it's an impure language, so expressions in this language may have side effects. It's strictly evaluated, so there is no such laziness as in Haskell, for instance. It's dynamically tied, but it doesn't have too many types. It has some built-in types like lists and tuples and records and maps, but no programmer-defined types. The main point behind Erlang is support to concurrency. So it has very cheap processes with the preemptive scheduling and provides message passing communication according to the actor model. And all these communication facilities extend very well to distributed programming as well. So you can just throw your processes on different nodes and you don't have to change too much on the code to have a distributed program. And fault tolerance is achieved by well-defined patterns, actually, which we call behaviors in the OTP standard library of Ericsson. Okay, so this is an example how an Erlang module looks like. This is a merge sort function, which I have placed in the msort.erl file. This is the sort file, and this is also the name of the module. And the interface of the module is the merge sort function, which has a single parameter. So this is this /1 at the end of the name. And let's see how this function is defined. It's a functional language, so we can use pattern matching. We define the merge sort with 3 alternatives. In the first case, we say that if we have an empty list, then it is sorted. You don't have to do anything, so we return the empty list. If we have a list with a single item, then we don't have to sort it again. We just return the list with the single item. Of course, the third case is the complicated one. So if you have any other lists, well, then we split them into 2 halves. So we use the standard library function list split. And using this function, we split L into 2 parts, roughly the same length. We just compute the length of the original list and divide it by 2. Sorry. Divided by 2. And then the resulting 2 lists, L1 and L2, can be recursively sorted and the results merged. Where the merge function is also defined using pattern matching. If you merge an empty list with a list, then the result is the list. If you merge a list with the empty list, then the result is again the list. And if you want to merge 2 non-empty lists, then you have to take the heads, the first items of these lists, H1 and H2, and you have to compare them. And of course, you start with the smaller of the 2, and then you continue with the rest of the list, merging the tail of the first and the second list, or merging the first list with the tail of the second list. So as you can see, this is very high level, very easy to program. The syntax might be a bit strange. You have to remember where you want to put semicolons and commas and full stops. But apart from that, I think it's quite readable and quite easy to write as well. So why Erlang? So why would you use Erlang in HPC? It's not really designed for HPC. Erlang is designed for scalable, faulty and distributed systems. It's more like a coordination language and not a number crunching language. In spite of that, there are some applications in Erlang in HPC. So some of our colleagues at AGH University in Poland work with Erlang as an HPC language. They design, for instance, an urban traffic simulation completely written in Erlang. And the results they have achieved are quite nice. So they investigated scalability, and yeah, it was really good, up to about 20,000 cores. that's actually an indication that the message passing style communication and the parallel patterns are really scalable. Okay, so let's go back to our example, to this merge sort function, and let's have a more detailed look at it. First, I would like to change this code a little bit. Here, the recursive calls, merge sort L1 and merge sort L2, I will change those. What I will do is I will use a higher order function to update L1 and L2 into S1 and S2. So the list map function is a higher order function, which takes another function, the merge sort function, which it calls on the items of the second list. So L1 and L2 is a list containing just 2 elements, and the list map will apply this merge sort function on those two lists. The result is again a list of lists, S1 and S2, and now we have to merge S1 and S2. So this is really the functional style of expressing things, and using higher order functions is a key in our DSL for parallel patterns as well. We will see soon that actually the implementation framework of the DSL is a higher order function. Using the built-in concurrency features of Erlang, we can of course very easily turn this merge sort into parallel. Well, this is a very naive implementation of a parallel merge sort, but the main ideas can be perceived here as well. So what we have done, we have spawned 2 new processes computing the sorted sublists. So we have this merge sort prots. This is the description of a process. So this function will be the main function of a process. And when we split up our original list L into L1 and L2, we started a new process which will work with L1 and another process which will work with L2. These processes will recursively sort the received lists and send back the result to another process. So this is message sending in Erlang. PID is the process identifier of some other process. So what we can see here is that the original process passes its own process ID to the spawned processes. So the result will be sent back to the original process, and the results are received using the receive construct of Erlang, like this. First we receive S1 and then we receive S2, and when we have both of the sorted sublists, then we can just merge them. So as you see, it's quite convenient in Erlang to write parallel code using the concurrency primitives, but if you go for bigger examples, then it turns out that this can be really cumbersome, and of course you have to really care about deadlocks, for instance. So we are seeking better ways to expressing parallelism. So what we would do instead, using Scala and its high-level patterns, is to use a higher order function which implements the divide and conquer behavior. So we say that if we have to sort a list, then we will call a specific instance of a divide and conquer algorithm on this list. So this SKHLP is the Scala with high-level patterns module, and it contains this DC higher order function, this divide and conquer function, for which you have to provide further functions. IsBase is a function which decides whether we are at the base level of the divide and conquer splitting of the original problem. Well, if our list is small enough, then yes, we are at the base. The base case is implemented with the identity function, so we don't have to sort a list which is either empty or has only a single element. The divider function is the next function. This is how we split up a big problem into two smaller sub-problems. So this contains the call to the list split function. And finally, we have a combiner function which will merge the results of the recursive sorting. So if you provide all these functions, then you can instantiate the divide and conquer pattern, and this will execute with the best performance that you can achieve using the skeleton library. So this is the preferred way. So we want programmers to work on parallelism in this style. Let's see some other examples. For instance, an example which merges images, which reads images from somewhere and merges them. So this is a very simple implementation, again, using the higher order function map, lists map. So what we do is we have a list of images and we want to process them all. And what are we going to do with one image? Well, we will apply this function for all of these images. So this function takes an image and it reads from some source and then applies another function on it. So this looks like a pipeline, doesn't it? So this is how we can rewrite this using Scala. We can say that one possible implementation of this problem is a pipeline. This is actually the pipeline we have seen on the previous slide. A pipeline with two stages, where both stages are implemented with task farms. And the task farms perform sequential components, these read image and convert merge functions. And this DSL program is executed with the scale-do higher order function on the inputs, on images. So this is how the deep embedding of our DSL takes place. Of course, this is not the only way that we can parallelize this simple application. A completely different pattern of parallelism can be given in the following way. Let's have a farm with 16 workers, and each worker will be a pipeline. So each worker will have a pipeline with two sequential stages. One stage for reading the image and the other stage for converting the image. That's also a feasible parallelization of the same program. And if you try to see what are the differences in performance among the different solutions, well, with this very simple example, everything was quite similar. The manually parallelized version was not actually the most efficient one. So Scala could beat the manually parallelized variant just slightly, but actually it could beat it. And the scalability was not very bad either. There are many other case studies where we investigated the applicability of the Scala library. In this evolutionary multi-agent system implementation by the AGH University in Poland, it turns out that if you try to turn your code as concurrent as possible, then of course it will not be the most efficient implementation, because in certain cases it is not worthwhile to introduce parallelism. So the best approach was to change the code at certain places, but not changing it at other places where also parallelization is possible, but it's not worthwhile. So that was the hybrid approach. And in this case study, the programmers selected very carefully where exactly parallelism can be injected into their application to get the best performance. Okay, so that's also an issue. So if I can parallelize an application in different ways, then how can I choose most conveniently the best parallelization of the application? Or can I experiment with the possibilities? Can I very easily reformulate my program with the different parallel patterns and measure whether the first or the second one is better? So this should be supported. This should be provided by the tools that we would like to develop. Okay, so let's see how we use Erlang to refactor programs to this embedded domain-specific pattern language. So we have developed in Erlang a refactoring tool, which provides about 30 refactoring transformations. It's not just a refactoring tool, by the way, it's also a static source code analysis tool, which allows programmers to comprehend the code structure. So this is, for instance, a dependence graph drawn for a standard Erlang-based application for the Amnesia distributed database management system. So these are the modules that are contained in the implementation of Amnesia, and this is how they are related to each other. So Refactoral has lots of micro refactorings. Some of them are already familiar from the previous slides. So these are the more or less language independent refactorings, like renaming and moving definitions, introducing and eliminating definitions, generalizing function. And then it has other refactorings which are more related to functional programming or more related to the Erlang programming language, like reordering and toppling functional parameters and introducing the record data type, or expanding fun expressions or transforming list comprehensions. So these are more paradigm-oriented refactorings. And atop of Refactoral, we have developed another refactoring tool, a variant, a branch of Refactoral, and this is Party, paraphrase refactoring tool for Erlang. And this Party tool is able to find pattern candidates in our code base. Pattern candidates are code fragments which are amenable for parallelization. So it's not the programmer's responsibility to go through all the lengthy code bases and find all the spots where parallelization is possible. The tool can help in this task to the programmer. And then the tool also can make suggestions where to apply parallelization, because at certain places it is not really worthwhile to parallelize the code. And finally, of course, the tool offers the suitable refactoring transformations which allow the programmer to change the sequential code into parallel using the parallel patterns of the SCAL DSL. So this is the main idea, the overview of the Party tool. So the user applies pattern discovery on some Erlang codes. So we have a huge code base on which we want to apply the pattern discovery first. And the pattern discovery will come up with candidates these are code fragments where a parallel pattern can be introduced. But we have to decide where to introduce our patterns first. So we have to rank the candidates. And we have different ways to rank the candidates. After we could rank the candidates, the prioritized candidates are presented to the user, and they can make a decision, for instance, to apply refactoring transformations with the tool, the refactoring engine, and change the code, or maybe do refactorings manually if that is preferred. I think a key issue here is how we could rank the candidates. And we have implemented two different ways. One is based on complexity metrics, and the other one is based on a very, very tricky benchmarking. It's dynamic benchmarking performed static time by artificially assembled input data. So I will tell you a few words about this later. Okay, so what is pattern candidate discovery? So pattern candidate discovery is actually a bunch of static source code analysis which run through our code and collects syntactic and semantic information and apply control flow analysis and data flow analysis and investigate function calls and recursive calls in the program. They build dependency graphs. They investigate side effects. Of course, if you have side effects at a certain point, then it's very hard to turn that code into parallel without the risk of messing up the side effects. So using this pattern candidate discovery, we can find the places where task farms, pipelines, divide and conquer patterns or reduce patterns can be introduced. And as we mentioned, this pattern candidate discovery will be accompanied by speed up predictions and a prioritization technique, so that we can make the best suggestions to the programmers where to apply refactorings. Well, let me show you a few examples. For instance, the image merge application. That's not a big application. That was just 700-800 lines of code and 100 function definitions in 6 files. But we could find a number of pattern candidates. Pattern candidates which were applications of library functions that we know that can be parallelized, like list maps or list comprehensions. It's very specific to functional languages, but again, something that is really amenable to parallelization. Or we could find function definitions in which the way recursion was applied allows us to change the definition into a parallel pattern, into a task form. The same analysis was carried over through on the evolutionary multi-agent system example. So in the EMAS system, we could also find lots of possibilities, more list comprehensions, 63 occurrences of list comprehensions with the possibility to transform it to forms. And then we investigated larger project. I mentioned already this NIJA distributed database management system. That's about 20,000 effective lines of code. And apart from the farm and reuse candidates, we could also find almost 60 candidates for divide and conquer. So divide and conquer candidates, I think, are the most interesting ones of all. And very similar results when applied our tool on itself. So we took one of the components of Refactoral, and it's also about 20,000 lines of code, and we could also identify many farm candidates and divide and conquer candidates. So what is a divide and conquer candidate, by the way? It's It's a function which directly or indirectly calls itself multiple times on the same execution path, like merge sort did. So merge sort called itself recursively twice. And also it's very important that the parameters of the recursive calls should not depend on the result of each other. So that's how we can perform the recursive calls at the same time. So these are the structures that we are seeking for divide and conquer candidates. So how do we prioritize candidates? As I said, one way to do this is using complexity metrics. That's quite standard solution. The more tricky approach is this benchmarking, which is completely done automatically and hidden from the programmer. So somehow we figure out the type of the parameters of functions, and somehow magically we generate possible input values and compile the program in the background and run it and test it and measure it. And based on the cost model, we come up with some predictions. So that's the main idea. Of course, it doesn't work at many places, but sometimes it works. So for instance, we had a matrix multiplication project where it was quite easy to find out that the inputs are matrices containing numbers. So that was very easy for the tool. So it could apply this technique of benchmarking. And according to the cost model, it made some suggestions where to introduce a task farm, because with 2 workers it could produce some speed up. So that's one way to rank the candidates. But as I mentioned, it only works if we are able to deduce the type of the parameters, and if we can automatically generate valid inputs for our functions. If this is not the case, then we can fall back to the second option and choose the best candidates based on some complexity matrix. So we can compute how, for instance, a modified McCabe metric can be used to argue whether one function is more complex than the others, so it makes better parameterization possibilities than the other one. And as you see, this is the user interface of our tool. This is the pattern candidate browser. Then you can select which transformations you would like to perform, and then you can, of course, apply the selected transformations by clicking this button. There are even more developed ways of finding the best pattern candidates. Colleagues at the Robert Goddard University use a technique they called performance enhancement infrastructure. They actually did not work with our Erlang environment. They used FastFlow, and they used the Monte Carlo tree search model to find the best static mapping of a parallel pattern on a heterogeneous hardware. I really don't know whether they finally managed to do the dynamic remapping, but that was also one of their goals, which is, I think, also a very important facility in this refactoring-based approach, that if we are able to refactor one pattern to another pattern, then dynamic remapping can actually be implemented under the hood in the runtime environment. So this was the methodology they proposed, and as you see, if you have an application, you can identify the initial structure, and then you can find out different configurations for a parallel execution, and then using a cost model, you can filter out those which look promising, and then you can apply some AI techniques to rank these configurations and find the best static mapping, and then you can use a refactoring tool to introduce the patterns, and then you can deploy your application on heterogeneous hardware. But let's go back to the other tool chain, our tool chain, with Erlang and the party tool. So we implemented lots of interesting refactoring transformations in party, ones for introducing the skeletons, the task farm, the pipeline, and so on, and ones for introducing the divide and conquer pattern, which is really complicated. And before you can do that, you have to perform lots of other transformations. So introducing the divide and conquer pattern is actually a lengthy sequence of small program transformations. And these are quite specific to Erlang, and they are sometimes quite specific to our goal of introducing the divide and conquer pattern. So it is a good idea to provide these refactorings in an extensible manner using a domain-specific language. So this is our last bullet point for today, how to define refactorings using the appropriate domain-specific languages. Okay, so if you look at what others do, you often see that refactoring transformations are defined in general purpose programming languages. So they sometimes put their hands on some abstract syntax tree and try to transform it. And this is not really maintainable, this is not really extensible, and it is not really generalizable. By the way, refactoral is defined in this way as well. So in refactoral, we have implemented in Erlang, in a general programming language, all our algorithms which transform, well, not just an AST, because we represent information in a more structured way using a semantic program graph. But the main idea is the same, that we have big, well, I can say monolithic implementation of a refactoring framework. And according to the predecessor refactoral, most of the party tool is also implemented in Erlang, in a general programming language, general purpose language. So some parts of the party tool could be rewritten already using a DSL. So I think that's very, very important for our future to move most of the refactorings into this DSL. There are actually ways to describe refactorings in a very general way. So there are formal methods, term rewriting, for instance, or graph rewriting, which provide the grounds for program transformation and formalization. Probably the most promising approach is strategic term rewriting. So this is what we try to follow. And then System S is a very nice formal language to describe rewritings. And AST transformations can be very easily programmed with Stratego, and the whole thing can be supported by a language workbench such as SpoofX. So there are many very nice tools to develop program transformations at a very high level. So these are a very solid basis for DSL. If you look at related work, it turns out that there are extensible DSLs around, like Jungle, or there is actually a domain-specific language for Erlang refactorings. It wasn't developed by us, but our colleagues in Canterbury. But we also work on this, so we have a prototype of such a domain-specific language, and others. So let me show our approach. This is actually a prototype, so some of party refactorings have been already implemented using this DSL, but we are now in the process of rewriting this into more advanced DSL. So the basic idea is that you have rules to apply, and rules are described in such a way that you have a pattern, a syntactic scheme for the old code, and then you have the expected outcome, a syntactic scheme for the new code. And you have conditions, of course, the site conditions. You have to investigate whether these conditions hold before applying the refactoring. So for instance, here is how we try to introduce a task farm. This is actually the first step of introducing a task farm. This refactoring is called normalize list comprehensions. And if you have a list comprehension like this, you can actually turn it into a sequence of 3 expressions. This expression, and that expression. And as you see, the last of these expressions is actually an invocation of the lists map higher order function. And this lists map says that you have to apply a function on the items of this list. Well, this is clearly the point where the subsequent refactoring can introduce a task farm. So we can very easily remove this list map call and introduce a call to scale-do with a task farm skeleton. So this is the preparatory step before introducing the task farm skeleton. And in this refactoring, we first compute all the data that are required for the application of the main function. So this is the first part of the resulting code. And then in the second part, we apply the function on the generated list. Okay, so this is, if you look at more carefully, you will see that this is actually a pipeline, or this can be very easily transformed into a pipeline with the second stage as a task farm. And here in the where clause, you can investigate whether it is possible to apply the transformation or not. And also you can bind meta variables here as well. So vars is a meta variable referring to all the variables that were bound in the generators and the filters of the list comprehensions, and also appearing among the variables of the head expression of our list. Okay, so as you see in this domain-specific language, the main idea is to apply syntactic transformations. This syntax should be transformed into that syntax, but also we have semantic functions which can query the semantic program graph, not just an AST, an abstract syntax tree, but also a semantic program graph to collect information based on which we can perform the refactoring. The main question is whether we trust in such refactorings. So how can we develop trust? Of course, if we have an open source refactoring tool, then we can investigate code quality and say that, okay, I trust this or not. But maybe it's better if we apply some kind of verification techniques, either testing based or proof based. Well, we want to shoot at the best possibilities. So we want to develop machine verifiable proofs for the correctness of refactoring transformations. So we want somehow to develop machine verifiable proofs in Kuckuk or Isabelle or any other proof assistants, which guarantee that a refactoring transformation will not change the semantics of the transformed program. There are papers in the literature dealing with this issue. So we are not the only researchers in this field, luckily. So our approach that we try to implement in the HARP project, this is high assurance refactoring project, that we want to combine DSLs and formal methods in such a way that we can describe program transformations which are executable in the DSL, and at the same time, they are verifiable using our formal methods. And we ground our solution on strategic term rewriting with semantic predicates, as you have seen. I don't have too much time, so I'm not going into details about how we designed this language. I just want to highlight two interesting issues. First, that we can apply skeleton-based refactoring, so we can define reusable schemes that can be customized and parameterized according to context. And these refactoring skeletons are parametrically proven correct. And when you instantiate them, then of course you can create not just a new concrete refactoring transformation, but also the structure of the proof of correctness for that particular refactoring transformation. And another highlight is that granularity is really, really important. So you can do verification easily if the components that you use are very small, so easily verifiable, and you compose them in a way that provenly correct refactoring steps composed together will yield, again, a provably correct composed refactoring. So for instance, when we want to introduce the divide and conquer pattern, well, we may apply 30 or something elementary transformations, all of them actually refactorings by themselves. Okay, so this is ongoing work. So we are still working on formalizing Erlang in Kuckuk, providing big step semantics, executable semantics. And another promising research is formalizing applicative matching logic, and then first embed Erlang into AML, applicative matching logic, and then use the proof system of AMLs to carry out equivalence proofs. So let me conclude. I argue that we really need trusted refactorings, and this is best achieved if we have machine verifiable proofs. But for that, we have to describe the semantics of programming languages in formal methods, in proof assistance, for instance. And we can verify language-specific and language-independent refactorings, but we have to include them in an extensible framework. So it's best to construct a refactoring DSL from these proven verified components. And the main idea here is to combine very, very small refactorings to bigger ones. Then, if we have trusted refactorings, then we can implement and prove refactorings for parallelization. So that's the next main issue. And of course, the best to do here again is to have a DSL for describing the parallel computations. And it's also very important to provide transformations between patterns. So if we have already refactored our code into some pattern, then it is easy to refactor it to another pattern. So this makes experimentation with the code more easy. And then when we have this, then we can of course provide an experimentation framework where programmers can investigate different parallelization possibilities, and they can measure which is the best. They can select the best candidates and apply refactorings at the best candidates. So this is the story that we do, and at the moment we are still working on the trusted refactoring part of this story. Well, thank you for your attention, and I'm ready to answer questions.
Thank you, Tamás. Very promising stuff. Questions, anyone? Either online or here live? We have one here locally.
Hi, and thanks for this presentation. Very interesting work and very, very practical. I have one comment and a related question. I've had the misfortune of using Xcode for the past, I think, 11 years. And its refactoring tools have been consistently and utterly and hopelessly and unsalvageably broken. So I have trust issues with automatic refactoring. And my question is regarding that. So basically you're refactoring DSL. By the way, I very much like the approach of defining the DSL for high-level refactorings, but it's basically a macro processor, as I understand. My question is this right? And if so, how do you ensure correctness, or how do you write correct refactorings when the expansion of the macro requires generating identifiers? Is it hygienic? Do you have some other kind of magic sauce for making this work? Thanks.
So what we do is formalize everything in Kuckuk. So the elementary transformations have a well-defined or should have a well-defined semantics. First of all, we have to define the semantics of the target language, say Erlangen in our case, but whatever language you have, first you have to describe somehow the semantics of this language so that you can, after that, reason about modifications and the semantic preserving nature of modifications. So that's already a very hard stuff. It's not easy to define the semantics of any programming language. It's even harder to define the semantics of a usable programming language. If you have a toy language, then it's okay. For a usable language, it's very, very hard to define precise semantics. Without that, it's very hard to argue about anything. So this is, I think, at this stage, we are at fundamental research. So I don't believe that in the next few years we will have really good verified refactorings for languages like Java. It's just too complicated. You can't even define the semantics of the language. I think it's not properly written, by the way. So if you look at the Java language specifications, it's a mess. So it's not a formal description of a programming language. So it's very hard to get to a point where you have reliable formal semantics of a programming language. But then, if you have that, then you can define the semantics of small transformations, and they can be proven correct. And of course, you say if you think about some small techniques like identifier generation, these are all big issues actually. Very small from the point of view of the whole thing, but all of them have to be covered, not just as a macro expansion or something low level source-to-source manipulation, but really well-established transformations at the semantic level. So this is what we believe. So we should not do macro processing. We should not do source-to-source transformations. That's not the right way. That's too low level. So we have to take the programs to be refactored and the refactoring transformations into a domain which is very well established, which is mathematically approachable, and then we can express our proofs on that level. And it's very, very hard to do that because it's very hard to map anything usable to that really abstract level. But without that, you will have just really unreliable transformations. I know I didn't respond to your question in full details because it would take me 2 days to answer it properly, but I really understand your point, and I really agree with you that it's a really hard business, and my opinion is that it's still years or tens of years to achieve our goals.
Thank you. I have another short question, hopefully. So in doing these transformations, can you or do you reason about data and locality, particularly in a distributed system, whether you send the data to someplace else or you do computations in place?
No, we didn't actually investigated that so far. No, I think that would be, again, a very interesting thing to do. Our refactorings are typically at the expression level at the moment. So in that case, every modification is made on local definitions and local data. Erlang is a share nothing language. So if you investigate a context, then you can be sure that the variables and the data used there is completely local to that process, and nobody else sees it. So it shouldn't be so race conditions and all this stuff, it cannot appear in Erlang. So maybe this is the reason that we so far did not really put an emphasis on investigating data locality issues.
So I think where you had this example of switching up the what was it, the farm and the pipeline, I think could be an example of this if it happens on the same inside the same.
Oh yes.
Then I guess it's the same process and there is no extra data movement.
Yes, in this case, yes, in this case, wow, okay, that's true. That when we use the cost model to predict which candidate is better than the others, we take into account that certain places copying of the data from the memory space of one process to the memory space of another process is necessary, or copying the data from one node to another node is necessary. So the cost, it is the task of the cost model to take care of this data locality issue. And when we use our benchmarking approach, we actually under the hood, we measure the cost of copying data. Okay, artificially generated data, but we measure the network bandwidth, the communication costs, and we use these measurements to instantiate the cost model, and this is how the cost model can take this into account when ranking the candidates.
Okay, thank you. We're a bit behind schedule. We're going to take a quick 5-minute break and resume at what is it, 11 with Fabio. So thank you very much, Tamás.
Thank you.
Be back in a few minutes. Okay, so next up we have Fabio Luporini from Devito Codes, formerly from Imperial College, who is going to tell us all about, well, Devito.
Hey, can you hear me?
Yes, looking good.
Can you see the slides? Yeah.
Yeah.
Good. Right. Okay, what time is it? Okay. So thanks for the introduction. So Devito. So I'll start with the motivation. So this is a project that started roughly, I think it's four years and a half ago at Imperial College. After a strong input from industry and from companies who essentially wanted to see whether it was feasible to build a new system based on DSLs to perform seismic imaging. So what is seismic imaging? So seismic imaging essentially is all about reconstructing the subsurface of some region. So for example, as you see here, the subsurface below a certain region of the ocean. And so the idea is to locate oil and gas below several layers of rocks. And how do you do that with seismic imaging? Well, there are several popular methods. Probably the most popular one is FWI, which is full waveform inversion. And these are really expensive methods. They're also fairly complex to write, actually extremely complex to write, and they are extremely expensive in terms of computational resources. So why DSLs? DSLs because so with these methods, essentially, you have to simulate the propagation of waves, so within some sort of computational domain. And simulating the propagation of waves means solving partial differential equations. So the idea was to build a system based on DSLs to express and solve numerically partial differential equations with the finite difference method, which is what is commonly used in this field. And so, and from there came Devito, essentially. So we sell it, we advertise it as a system which is able to generate production grade wave propagators. But in fact, over time, it has evolved into a much more general system that can solve any sort of partial differential equation and many other kind of operators too. And so it started off with seismic imaging. Now we also have interest in medical imaging and more generally machine learning. And what you see here in bold, essentially, this is like the key reason why this project began. So that there's a skills knowledge gap between geophysicists, data scientists, and HPC developers and the field of seismic imaging. And the idea with a system based on DSLs was to, to gather together people with different expertise to provide a system, to provide a software to essentially simplify the life of people. Okay, so I just want to convince you here that FWI is really, really expensive. So if you take real life FWI, it's not so rare finding yourself in need to perform methods where at each time iteration you have to perform thousands of flops because you are typically running high order methods, typically over very big grids for many time steps. And so if you put all the numbers that you see here in this slide together, you may need to perform even billions of teraflops to do one reconstruction of the subsurface through FWI. And that could mean from days to months of compute time on supercomputers. So this is, as I said, these methods are not just difficult to implement, but also extremely challenging to optimize. Okay, probably you all of you in the audience know about this stuff, so I'll be very quick. underlying idea with Devito and virtually any other DSLs is to raise the level of abstraction. And so instead of writing C code or Fortran code directly, which can easily become unmaintainable, we want to do things differently with the DSL. And in the case of Devito, what we provide to the users is a symbolic language, which is based on, which is embedded in Python. And as you can see here, if this is the PDE that I want to solve, this is my acoustic wave equation, for example, and this is my symbolic language. You can see that there's a one-to-one relationship between the terms that you see here and the terms that you see here in the PDE. And I'm going to show you a few more examples later on. But yeah, so that's the symbolic language. And then through Devito, we take the symbolic specification, we run it through the compiler and generate code. Okay, so probably one of the key differences between Devito and the talks that we've seen so far is that with Devito, the user writes the partial differential equations. So it works at a higher level of abstraction. I'm not saying whether it's better or worse. I'm just stating the fact. Okay, so this is a difference. And of course, okay, so why raising the level of abstraction is so important, specifically in the field of seismic imaging? Well, first of all, because R&D is still super active in this field. There are many formulations of the wave equations that are currently studied and improved and tweaked and so on and so forth. Many kind of space and time discretizations. The boundary conditions are a big beast in this field. There are many. And last but not least, as you all know, the proliferation of computer architectures. Okay, so there's a lot of variation in physics, in the mathematics, in the platforms, and so raising the level of abstraction can be is seen by sort of, you know, everybody today as, you know, the way to go. So just to avoid any ambiguity, so Devito is a DSL and compiler to solve partial differential equations through explicit finite differences. As I said before, it's not limited to solving partial differential equations, but that's by far the most important task. So it's implemented in Python. That means it's easy to learn, especially for the geophysicists or for any, you know, domain expert. The compiler today can generate vector code, shared memory parallel code. It can also generate OpenMP5 and OpenACC code to offload the computation on the GPUs. And it does support MPI, so distributed execution of CPUs and GPUs. It's easily composable with all of the other popular Python packages, such as PyTorch for machine learning, or even NumPy, Dusk. This is especially useful for seismic imaging. It's open source. It's completely open source. And well, maybe I should talk about this now. Okay, now, so and basically it uses, so since the very beginning, the best practices in software engineering. So we've got an extensive test suite. We do continuous integration. We have documentation, lots of tutorials. We do code reviewing on pull requests and so on and so forth. And this is probably one of the key strengths. So just some numbers. As I said, it started off in 2016. Today we have Devito version 4.2.3. The core compiler is roughly 20,000 lines of code. We've got a huge number of tests, as you can see here, which we test regularly through continuous integration. We have many tutorials there's a fairly large number of contributors to the code base. And in terms of users, so this project is financially supported by several companies, and the most important of which is DUG, Down Under Geosolution, which is essentially the company who helped us making the jump from being an academic level DSL to being a production level DSL. There are open source ongoing collaborations with other companies, and we have several groups around the world who are using Devito. And there's a relatively large community on Slack with almost roughly 400 people that talk about Devito and the future of Devito. So very quickly, and then I'll get to the technical stuff. So this is the timeline. This is more for future reference. All I wanted to show you here, well, this is just like this line here is remarking what I said before. That from the very beginning, we've pushed hard on testing and continuous integration. But this phase here between 2017 and 2018, this is basically when Devito became an actual compiler. And again, this was with the great help of DUG. And then over time, we've extended the DSL with more and more features, such as staggered grids, subdomains. This was here between 2018 and 2019. MPI, the intermediate representation of the compiler has become more and more robust. Yeah, and then many other features. In 2020, finally, we got MPI plus CPUs plus GPUs. And the future, well, we have a few things in mind, but maybe that's for future discussion. Okay, so as promised, the technical stuff. I have a notebook to show you here. I'm trying to make this less boring. So can you all see this? I think you can, right? István, give me feedback.
Yes, we can.
Okay, cute. And okay, so what is Devito? I'm gonna show you. So first of all, some imports from Devito. I guess all of you are familiar with Python, and if not, I think you should be able to follow me anyway in this tutorial because it's really basic stuff. So I'm importing stuff from both Devito and SymPy because SymPy is the package that is one of the key packages that Devito builds on. First thing we want to do, since we are in the business of solving partial differential equations, we want to create a computational grid which represents the domain of the PDE.
Fabio, sorry, can you increase font size?
Yeah. How is it now?
Yeah, thanks, good.
Now it's fine.
Good, yes, thanks.
So I was saying, this is the computational grid of the PDEs that we want to solve, and how do we create it? It's this line here. So we create a grid with 2 dimensions. The size is 5 along X and 6 along Y. That means that our grid has 30 points, and this is just the physical extent. Okay, so now we have our grid, and what we can do now, we can create functions on our grid. So these are a function is an object that we will use to express our partial differential equation. So I create a function over my grid. The function has name f. It's defined over this grid. And so what we get here is a function f over x and y. Functions carry data. Since the grid is 5 times 6, here we've got 30 points over 2 dimensions. Okay, nothing surprising. We can also define time functions because we are going to express time marching methods. So we need the concept of time. So time function is essentially a shortcut to build a function with a time dimension. So now I have G over my grid, but as you can see here, I have this t, which represents my time dimension. I can also take a look at the shape of G, which is 5 and 6 in X and Y, and 2 in time. 2 because you need at least 2 points to build a time marching method. As I said before, Devito, or well, actually, what I want to convince you about now is that Devito is super flexible when it gets to dimensions. So X and Y are the grid dimensions, but I can also create any other sort of dimensions. So for example, D, and here I've got my function U1, just like F and G, but now I'm supplying D explicitly. So now I have a function U1 over D, X and Y, so U, D, X, Y. And when I build my partial differential equation, I can mix up functions, time functions, custom functions like this all together. So that's not an issue for Devito. The only rule is that, I'm going to read it now, it must be possible to construct an ordering of dimensions. What do I mean by that? So look at this expression here. So I've got cos G times F plus sin U1. And as you can see here, X precedes Y in both G and U. But in this expression here, we've got XY here and YX in this U, which is this U2. Because as I did in cell 9 here, my dimensions were provided in the order YXD. So this is not okay to Devito, because the order, it must be possible to Devito to construct a deterministic ordering of dimensions. And why is that important? Well, this, you can think of it as a minor detail, to be honest, but this is important because what the Devito compiler does, what the Devito compiler relies on is data dependence analysis. And for data dependence analysis to not explode in complexity, it's important to honor this property. So this is the only rule. And if you keep this rule in mind, then with Devito, you can create any sort of expressions you like, any sort of PDEs, and you can compose expressions in any sort of way. Okay. So far, I've got my grid, I've got my functions, and then since I'm doing finite differences, I have to take derivatives of functions. So for example, here, I'm taking the first order derivative in X of my function F, while here, I have a spatial order 2 function H, meaning that I can take higher order derivatives, and in particular, through dot dx2, as you may imagine, I'm taking the second order derivative along x of h. So no surprises so far. And I can also take a look at the stencil that Devito will generate for these derivatives. So f.dx is going to have this stencil, and h.dx2 is going to have this stencil. So for those of you who are a bit familiar with finite differences, this should be no surprise at all, okay? I'm just stating the obvious, but basically I just want to draw an analogy between what you can do with Devito, with the symbolic language in Devito, and and the actual maths, okay, and the actual finite differences. I can of course take time derivatives. I can take a symbolic representation of my function, of my time function g at the subsequent time step, gt plus dt, because at the end of the day, that's what I need to express a time marching method. And I'm going to show you an example in a few minutes. Same for the backwards direction. and there's nothing stopping me to take time derivatives or space derivatives at gt plus dt. So this is totally legal with Devito. And why is that important? Because this is exactly what you got to do with typical partial differential equations. So that's the sort of expressions you need to be able to express. And there also are shortcuts for classic differential operators. So for example, the Laplacian, which is of course equivalent to the sum of the second order of the partial derivatives of h. Okay. Some advanced features very quickly. So I can also take derivatives of arbitrary expressions, so not just derivatives of functions. So this is an expression which has no physical meaning, but still I'm showing it to you because I just want to show you that I can do dot dx2 of this whole expression, and I can generate a stencil for this, which gets pretty ugly, you may say. But this is handy, right? Because if you have something complex to write, I mean, you as a user, if you have something complex to write, some high order stencils, for example, if you do it symbolically, you can easily see that it gets way, way easier. Okay. And here's another feature. Since a few months, maybe a year, we also have support for tensor objects, which is particularly appreciated if you are solving a tensorial partial differential equation, such as virtually all of the formulations of the elastic wave equations. So I have my tensor function A with 4 components. This is a 2x2 matrix. I have my vector function V consisting of 2 elements. I can take the product of the two, and unsurprisingly, here I'm getting the matrix vector product. And I can also apply other differential operators to B, so to the result of the multiplication. So for example, here I'm taking the divergence, which is going to produce this object here. Okay. So this was just to show you, to convince you of the flexibility of the language, to convince you of the fact that we can express virtually any sort of partial differential equations. And now again, very quickly, an example, because so far I've shown you how to express expressions, how to take finite differences of expressions. I'm going to show you how to solve an actual PDE, a trivial one, really trivial one, a linear convection operator. So I have my grid, 2-dimensional grid. I have my time function. Oops, this is an error. Thanks God, I spotted it. I execute the cell. So I'm initializing the field with this pretty smooth curve that you see here. Okay. This is the partial differential equation that I want to implement. How do I do that with Devito? You don't need to be an expert in physics or not even in mathematics to write this with Devito, because all you need to know is that this is the derivative of u with respect to time. And so you can type it explicitly here. You see u dot dt plus c, the left derivative of u in x, and so on and so forth, equals to 0. So this is exactly this equation here. Okay. Then what do I need? Well, I need to obtain a time marching method out of this equation. So how do I do that? I know that u dot forward is an expression for u at the next time step. So I create a new equation where the left-hand side is my u dot forward. And then I solve this equation with respect to u dot forward. So what happens if I do that? If I do that, I get this expression here, which is essentially what I need for my time marching method. So Devito does the magic, essentially. And then we feed an operator, which is the keyword, the main keyword in Devito, with this stencil. Okay, now I have an operator. By creating an operator, I'm triggering compilation. So what I mean by that is that I'm translating the symbolic specification into C. And I can also take a look at this code. Okay, so this was a trivial operator with just one equation, and the PD was pretty trivial. So the code that we see here also is pretty trivial. So bear with me, but what you see here, for example, is the time loop, and then two loops over our grid, X and Y, and then our discretized expression. And I can also execute this code directly from Python for 100 time steps, for example. And this is the result of the simulation. Okay, so this was, just to show you what Devito looks like. And it's the first time I use a notebook like this to show this stuff, because previously, in all of the previous talks, I was using slides, but then I easily found out that that gets quickly too boring. So give me feedback at the end of this talk, whether you liked it or not, because I'll use it for the next talks. And of course, this was a simplistic example, okay? So basically, I didn't show, I haven't shown any of the key features in Devito, such as subdomains or conditionals, or, well, most importantly, boundary conditions, stagger grids, and so on and so forth. Well, sparse operators also are a pretty fundamental feature. I haven't shown it because in the next talk, George is going to be talking about it. And very quickly, just want to show you how quickly it is to get parallel code. So for example, if I want to have, if I want to get OpenMP code, all I need to do is to add OpenMP language equals OpenMP to my operator. And what you see here is that I have the same code as before, but now I have OpenMP pragmas for shared memory parallelism. For CPU, if I want GPU code, I have to specify the platform. So for example, this is NVIDIA, for an NVIDIA card. If I want OpenACC instead of OpenMP, all I have to do is to write OpenACC here. And what I have here is my pragma ACC parallel loop, since the compiler, Devito, found out that X and Y are parallel loops. And it did that through data dependence analysis. And that's the end of the notebook, essentially. So now, where do I have my slides? Here. So at a very high level, so I showed you what Devito looks like. In a typical Devito program, what you have is a number of operators. And each operator can have any number of equations. And this is the structure of a typical seismic imaging code, by the way. So you do everything in Python, and then the compiler takes each of these operators and produces C code. This is human readable code, by the way, and this is a key feature, as Gihan was explaining yesterday in his talk. This is a key feature to convince people about what you are actually doing. And it also gives people the possibility of, well, first of all, checking their Python implementation. And secondly, to customize this code and to edit this code to, for example, quickly try other optimizations without having to learn anything about the compiler. And then we create shared objects. So this means that there are two execution models with Devito. One is directly from Python, So you do everything in Python. The other one is that you use Python to generate this code, these shared objects. And then you have, for example, some legacy code, and then you just link these shared objects to your legacy code so that you can basically exploit Devito for the wave propagators while the rest remains the same. And this was a killer feature for the companies who are supporting us, by the way. So I won't have time to go through the whole compilation pipeline, but I at least want to show you how it looks like. I'm not pretending you to neither read anything here nor understanding what's going on, but just to give you an idea. So this is the operator, like the one that we wrote before, which takes as input a number of equations. So we create an operator, and then the compilation takes place, and it goes through 1, 2, 3, 4, 5, 6, 7, roughly 8 macro compilation stages. Now, one of the key things in Devito is that most of the performance optimizations happen on an intermediate representation where there's no abstract syntax tree. So they happen at a very high level of abstraction. And in particular, they happen here at the level of the clusters. So a cluster is a collection of equations. So a cluster is essentially a collection of equations which eventually will be scheduled within the same set of loops. So it's a loop nest, but it's a very high level representation of this loop nest. So most of the key optimizations, including what we call a loop fusion or loop fission or blocking and many others, they all happen on this representation. And this has fundamental implications on the software engineering, because doing optimizations at this level is much, much easier than doing optimizations at this level, where we do have an abstract syntax tree, because sooner or later, you know, we have to build a tree representing the code that we are going to generate. So yeah, I just wanted to highlight this fact, and to get to this particular intermediate representation, it took quite a few years. And so yeah, this is probably one of the key things. As I said, I don't have time to go into further details, but we can talk offline, of course. But yeah, from a software engineering perspective, this is probably the killer feature. All right, so I'm going to get back to my slides. I just want to talk very quickly about the performance optimizations we do. We do all of the classic optimizations for stencils. So loop blocking, we do classic loop blocking. We also do hierarchical blocking. We do overlapped tiling, as I'm going to show you next. And we are also going to do time tiling, as George is going to talk about in the next talk. We do fusion, we do fission, we do code motion. And of course, we do vectorization and shared memory parallelism. We also do a series of flop reduction transformations. So transformations to reduce the arithmetic complexity of the stencils. Because one of the common misconceptions is that if you have a stencil, then you are going to be memory bound. So all you need to care about are memory optimizations, such as blocking. Now, this is true if all you care about is a low order method. But if you do care about high order methods, and we do care about high order methods in seismic, for example, then your stencils can get larger and larger. And since you are taking derivatives, because we are doing through finite differences, if you don't perform the right set of transformations, you can easily generate codes with thousands of flops. And if you do that, then your kernels will be compute bound, and that's an issue. So we've added to Devito a series of more or less conventional transformations to reduce the flop count. So some of them are fairly classic, like common sub-expressions elimination, constant folding. We also do factorization, and most importantly, we do this guy here. So cross-iteration redundancies elimination, which I'm going to show you in the next slide. And just to conclude here, we also support a number of classic optimizations for MPI, such as computation communication overlap. So cross-iteration redundancies elimination, as I said, why do we need, so before telling you what this optimization does, I want to tell you why we need it. Well, we need it because as I anticipated, we need to take derivatives of some sort of expressions. And as soon as you take derivatives, you generate stencils which may look like this one here. If you pay close attention to this expression here, you see that there are three terms, but this term here, sine phi ij, will produce a value which is exactly identical to the value produced by this term in the previous iterations. So there are redundancies. So in Devito, we have a fairly sophisticated piece of code or compilation pass, or actually collection of compilation passes that spots all of these redundancies and produce a new schedule of expressions. And in this example here, which is of course a trivial example, what the compiler would do is that it sees that sine phi ij is a redundancy. So it assigns it to a tensor temporary, bij in this case. And then it replaces each occurrence of the term with bij with suitable indices. And this is key to reducing the flop count. This is absolutely fundamental to reduce the flop count. Of course, we are also introducing a trade-off. I mean, there's a delicate trade-off to be taken into account, because by reducing the number, it is true on one hand that by doing that we reduce the number of flops, but we are also increasing the memory footprint, of course, because we are introducing a new temporary here. And this analysis is performed by the compiler itself. Yeah, I just want to show you very quickly through an example how this cross-iteration redundancy elimination composes nicely with overlapped tiling. I'm not pretending you to understand what's going on here in this excerpt, but bear with me for a moment. Here, we have a first loop nest over x and y and z, which is computing two temporaries, R47 and R52. Now, these two temporaries, they were produced by the cross-iteration redundancy elimination pass. Subsequently, we have another loop nest, which is going to read from R47 and R52. Now, what we see here, there are two outer loops over x and y, in particular over x blocks and y blocks. And the two inner loop nests, the first one computing the temporaries and the second one reading from the temporaries, they are both sharing the outer loops. And that is possible. So this sort of fusion is possible through overlapped tiling. And this is absolutely crucial to get the best possible performance out of this code. And this excerpt here, by the way, is extracted from one of the production grade wave propagators that was implemented on top of the Devito. So this was TTI in particular. But anyway, so very quickly, since I'm running out of time, so some performance numbers. So these are fairly old results from a couple of years ago on a Skylake 8180. These are the results from an isotropic acoustic wave propagator. We call it production grade wave propagator because it's not just the finite difference stencil. What we have here, I mean, I haven't shown it to you because we don't have time, but what we have in this kernel here is the finite difference stencil, the boundary conditions, the injection, like the loops to inject the waves, the loops that record the values of the waves at certain grid points, the so-called receivers. And many of these loops are non-affine. So they are non-structured in the sense that it's like they are loops over sets within directions and everything. So this is the performance of, complete wave propagators. This is the performance for 4 different orders, for 4 different space orders, 4, 8, 12, and 16. And as you can see here in this roofline, we are achieving a decent fraction of the attainable peak on a fairly beefy Skylake. Same story, but with TTI. Now, this plot here is a bit verbose. I'm not pretending you to understand it, but I just want you to realize the importance of the flop reducing transformations that I was talking about before. So the red dots is essentially without or with just a few flop reducing transformations. And the green ones is TTI with Devito with all of the flop reducing transformations enabled. And as you can see here, by applying these transformations, we are reducing the operational intensity of these kernels, but we are also reducing the execution time. So we are making these codes more memory bound, but in practice, since we are reducing the flop count, we are also reducing the execution time by bringing the flop count from, for example, thousands of operations to just a few hundreds. So for example, the red triangle here, so no optimizations, was almost 500 seconds, and we brought it down to 160 seconds. This is ongoing work that we are doing with Chevron. So at Chevron, they are playing with Devito. They have re-implemented most of their core wave propagators on top of Devito. And they are running comparisons against their R&D codes, and they are achieving fairly good results. In fact, we have Devito beating most of their codes. Again, I'm not pretending you to understand exactly what's going on with these numbers here, but the key idea is that all of these dots are slightly different implementations of the same wave propagator with Devito. except for one dot, which is this. So the circle dots is their code, is their, handwritten C++ code. All of the other dots are Devito for 3 different kind of wave propagators. So isotropic, acoustic, VTI, and TTI. And in all of them, we have Devito taking the lead. Again, this is ongoing work, but it's open source, so that's good. And this is just quickly, and then I'm done. This is just some statistics. You know that Devito is used by DagWave in DagWave, which is their production code. So this is numbers that I've got from Doug just yesterday. So in their cluster, which comprises a huge number of KNLs, over the last 90 days, on average, 1,300 KNL nodes were running DagWave, and therefore Devito, because they only use Devito to implement the wave propagators at any given time. And this is equivalent to 4 petaflops of double precision at peak. And this is just single node. So each KNL is running DagWave in shared memory. Soon, they are going to be using MPI for production as well. They have some early results showing up to 80% parallel efficiency on 4 nodes, but we still have to do, a lot of tuning here. So this is, preliminary results, but we're getting there. And the bottom line is that soon we will have Devito in production runs over MPI as well. MPI support, I promised I was done, and that really is the case, because all I want to say is that if you, I've shown you the symbolic language in Devito. If at some point you decide that you want to run with MPI, all you need to do is to just run with MPI run, and automatically everything will still work. Modulo, a few tweaks here and there. For example, if you're plotting stuff, or if you have to do parallel I/O and this sort of stuff. But those issues are orthogonal to Devito. For Devito itself, all you got to do is to MPI run, Python your code, and then everything will just work. After some extensive software engineering in the guts of Devito. Okay, again, these are the companies who are financially supporting us. Running out of time, so I'll let you read through the conclusions. But the most important thing is this red sentence here. So Devito is an interdisciplinary, interinstitutional, international open source effort, which was only possible because we managed to gather together many different people with many different backgrounds. So geophysicists, experts in physics, in mathematics, in computer science, HPC experts, and so on and so forth. It's through these, it's through all these different expertise that we managed to get to this point. And yeah, that's it.
Really cool stuff, Fabio. Thank you. Any questions from anybody? I have a whole bunch.
I just found.
Okay, so let me start with one. This is more a high-level question. So at the beginning, you mentioned you have really big meshes, like 1,000 cubes. But I guess all the interesting stuff happens at the interfaces or the boundaries between different layers of rocks and such.
Yeah.
So have you, or is there any literature even on either adaptive mesh refinement or unstructured meshes or something like that, which would reduce this cost?
Yeah, I mean, yeah, that's a good question. So the literature is vast, to say the least, and there are all sorts of numerical schemes to deal with that kind of stuff. One of the key, and that applies to both unstructured and structured meshes, to be honest. One of the key things that we want to do with some of our users is to start exploiting subdomains to run different physics in different layers of the domain. So for example, if all you need to do is to model the propagation of the wave in the C layer, then you can get away with a fairly simplistic physics, which means not so computationally expensive. As soon as you get through the several layers of rocks, you may want to start running something more sophisticated, such as TTI, which is more expensive, of course. And as you said, something pretty clever needs to happen at the interface between these subdomains. And that's a question that only the experts in the numerical methods can answer. Definitely not me, but basically what I do know is that, and as you probably imagine, what we do need is some sort of, of interpolation between what happens in one layer and what happens in the next layer, or some sort of coupling, some sort of equations to couple, what happens here with what happens here. And of course, this is not specific to seismic in any way. Okay? We find this in many other fields that applies to unstructured meshes too. So yeah, I don't know if that answers your question, but
mostly, yeah. Sebastian has a question.
Yeah, so thank you very much for the nice talk. I especially enjoyed the live demonstration. It was very insightful. To my question, so I see you are applying a lot of very aggressive optimizations, and I would imagine that this could change up the order of the operations performed. And if you do CSE, then this, of course, goes into the same direction. And the question would be, does this change the outcome or the result of your simulation, especially if you're doing explicit time integration? And is this a problem for your users? Because you've said in the beginning, they are very fond of this code that they can verify. But of course, if they have a look at the optimized code, they won't be able to do that anymore. Right?
Yeah, absolutely. So, well, at the end of the day, so now I'm talking about the field of seismic, okay? Seismic imaging. So at the end of the day, what these guys, like what the users want is to be able to pass the so-called adjoint test. That gives them, without getting too much into the details, but there's a range of higher level tests. And if they pass, then it means that your wave propagations, both the forward propagation and the backward propagation, are doing the right thing. Now, more specifically about your question, you are absolutely correct that some of these transformations here can alter the numerical output. Over the summer, so not so long ago, we actually spent virtually our whole team spent a significant amount of time chasing numerical discrepancies due to the scheduling of the arithmetic operations. So what do we do essentially? Well, yeah, we know that this is the price to pay, that some of these passes we can alter the numerical output. We provide an option, which is essentially the equivalent of, for example, ICC and GCC have the safe math mode, avoid all of the optimizations that can alter the numerical output. So we provide these sort of options to optionally disable some of these passes should people be in need to regain the accuracy or to check whether the loss of accuracy is due to some of these transformations. But what I can tell you is that 95% of the codes that I know of built on top of Devito, they can run safely and pass the adjoint test with all of these transformations. And also we always, when we JIT compile the code with GCC or ICC, we keep all of the math unsafe optimizations enabled. We flush the normals and we do all of these things. So by default, we are extremely aggressive in terms of restructuring the mathematical expressions. But optionally, users can back off and disable groups of these transformations, essentially.
Do you do mixed precision to address any of these issues?
No, we don't do mixed precision, but it's been on our roadmap for a while, and probably next year we're going to do something about that. Do you?
Not automatically, no. But that is actually something we are going to look at soon.
So,
looking at one of the students,
yeah.
so he's supposed to be looking at this. So fundamentally, or in most cases, you use single precision.
Well, for seismic imaging, yes, because that's what these people use, and because they do that because essentially, as in this slide, I was talking about the flops, but it's not just about the flops, it's also about the memory footprint. And if you take TTI, which is a super sophisticated physics, you've got tens of fields, and if you don't do floats, well, your memory footprint doubles. And with float, it's already fairly significant. And with double, it explodes. So people, like users in this field, geophysicists, are happy to run with single precision for performance reasons, and they accept the results they get with float, essentially.
And since precision, how about half precision?
I was talking about this exact stuff about half precision with Gerard yesterday. I guess you're asking because of all of the upcoming architectures which seem, for machine learning, for example, which have specialized hardware for half precision. We've been talking about it, and the thing is, there's literature already in seismic that shows that certain classes of problems seems to be doing fine with half precision. So we may actually want to spend some time in the next months working on that. As I said, I was talking about this stuff, it was yesterday. And well, I think it boils down to our funders at the end of the day to see what their needs are. But it's been, this idea has been floating around for a while, and we were talking about it these past few days. So.
Okay, thank you. I still have a page full of questions, but it's unfortunately time to move on. Well, fortunately, because we have another very interesting topic. We'll have George Bisbas from Imperial College London take a deeper dive into some of these optimizations in Devito. So thank you, Fabio. And George, you should be able to share your screen now. Yeah, looks good.
Hi there. Hi, everybody. Can you hear me all fine?
Perfect.
Yes.
Thank you very much. And I guess you can see my shared screen. I just want to make sure that you can see my mouse pointer as well.
We can see that too. Yeah.
Perfect. Okay. Thank you very much. And thank you. I'm really glad to be here today. So I can talk about my work on temporal blocking of finite difference stencil operators with sparse off-the-grid sources in Devito. So you saw earlier in Fabio's talk that what Devito DSL is capable of doing, and you also saw a range of wave propagators that can be modeled through Devito. We all know, however, that all these practical industry level simulations are complicated and very expensive, as you saw before. And there was also a mention on the sparse operations that Devito is capable of handling. And today we're going to talk about these sparse off-the-grid operators. Concerning the terminology, maybe off-the-grid terminology is not, maybe we're not all familiar with this, but we'll explain later what this is about. And so these operators drive us a bit away from the typical stencil benchmarks that we encounter. And we'll also talk about temporal blocking, that in these cases is a bit challenging to apply and not straightforward. And we'll showcase our approach in order to be able to overcome these limitations and give a performance boost. So as the title of this workshop suggests, we talk about domain-specific language in high-performance computing. Well, these red blocks here are an oversimplifications of what you saw before, of how we start in Devito from a high-level DSL specification to high-performance computer-generated code. This is the current status, and my work is trying to get a bit more on, to raise a bit more the performance bar of the generated code through applying temporal blocking. So quite a few things that I will mention now have been already discussed over the past talks, so I'll be brief in some of them. So you know that PDs are everywhere in a range of scientific applications, from CFDs, image processing, seismic and medical imaging, and weather forecasting, as we saw yesterday in two very interesting talks. And through the finite difference methods, we're able to approximate them and solve them. And you also saw in the previous talk how Devito is able to generate all these stencils and HPC code from the symbolic specification. Our goal here is to improve this performance, and just a quick peek of the overarching application in seismic imaging. So maybe I'll have to skip quickly these slides because we saw that before. Stencils are everywhere, ranging from simplistic one-dimensional three-point Jacobi's to wider on 3D and more dimensions. Thick halos are always sometimes needed to ensure that out-of-bound axes are all fine. A vast literature on optimizing them, and a lot of parallelization, as well as shared memory and parallelism and distributed memory as well, with OpenMP vectorization and MPI. And now we get to the point that we need to talk about the modeling of practical applications. We saw that we usually have these these sparse operations that Fabio mentioned a bit earlier. So when we have these sparse operations, it's clear that not only stencils are the game, not only the typical stencil update where we sweep over the 3D grid and update some points. These yield non-conventional update patterns. And if we have a look at the bottom right pictures here, we know that these are usually points, red color here, these points, that are not aligned with our computational grid. Like they are not aligned with the black points here in the edges of the squares, that these points have the spacing in X and Y. So we iterate them in a different way. And before we go there to show some code, let's have a very quick look of how exactly these operators look alike. So we have this typical problem of seismic inversion where an exploratory ship injects here acoustic waves into the bottom of the subsurface, and with hydrophones it's receiving measurements in order to be able to reconstruct the subsurface. And when we try to model that with the finite difference methods, we have the finite difference grid that is applied all over the physical domain that we are trying to study. You can see the edges here and with the blue points. And the sparse operators as we said in our modeling, are usually not aligned here. With the red point, you can see the source, with the yellow ones, for example, the hydrophones. And usually they yield some complex data dependencies in our generated codes, in our kernel codes, that we need to treat them in some special way in the points that they affect, so that we're able to apply some of our optimizations. So you can see here with light red color some points that are affected through these operations. Let's have a quick look at code here to see how exactly are these sparse operations modeled. We saw some pseudocode here where we have a time-stepping loop, okay, a time loop, the typical kernel update of a toy, or not a toy listed, but a Laplacian Jacobi-like stencil that we sweep over x, y, and z dimensions. And what we usually do for these sparse operations is that we iterate over a set of sources, that each one of them holds the coordinates of it in the 3D space, and then by identifying, by discovering the points that are affected, we use a mapping function to inject the part of the source injection contribution in the points that are affected. So as we saw in the previous slide, the open red color here. Sorry to go back. This injection is aligned in time, however not in space, as we saw before, and this causes problems in applying some optimizations. We'll explain them in the following slides. Here I have a bit of an extended pseudocode compared to the one we saw previous concerning source injection. So I will explain a bit more here what I said before, that for each source we iterate using its coordinates to find the minimum and the maximum. It's like the affected points in the surrounding square or cube. I mean, depending on whether we talk about 2D or 3D space, we usually talk about 3D space. Then we calculate the weights of impact using the source coordinates and the offset from the points that are affected. And then we usually have unrolled loops because we have sparse operations as well, that for 8 points, we able to calculate the injection part of each sparse operation and apply that to the points that should be affected. Now, we had a look already about how are usually these sparse operations modeled in general in codes that are doing this these wave propagator simulations. And now we'll talk about some things that probably most of the attendees are aware about. Applying space blocking to these codes is has no problems. Is one of the optimizations that Fabio already mentioned in the previous talk. And we are able to apply that without problems because we talk about data dependencies that are located in the same time loop, because sparse operations are aligned in time. So in this picture, I'm showing these sparse operations with the red diamonds. Of course, it's a 1D simplified example because it's complex enough to show that in a 3D real case, how it's affecting the neighboring points in the time-stepping updates. So there are no data dependency violations when applying space blocking. Of course, rich literature of how we can optimize that for several stencil codes. Now, another well-known optimization is temporal blocking. Space blocking, however, this is extended in time dimension. We try to exploit reuse towards time dimension. So we try to, instead of doing a full sweep for one time step over the whole grid or over one dimension at a time, we try to build, to forward our simulation in time whenever this is considered applicable in space and time. So when the data dependencies allow us to do it. And of course, there is rich literature behind that, several variants of temporal blocking. In our talk today, we're going to use as a proof of concept one of the simplest, well, not simplest, but one of the easier to conceive, at least geometrically, approaches, that is the wavefront in skewing. The wavefront or skewing, like similar enough they are, concerning temporal blocking, like a typical picture of it you can see in the figure in the bottom left, where after, for example, we have been able to update at time equals 0 the points at x equals 1 and x equals 1, we are able, through the data dependencies that are satisfied, to compute the point at x equals 0 and time equals 1. And the same goes on for the next tile, for the orange or yellow. I'm not sure how it seems to be in the next tile. A lot of work has been done on this front. Like one of the papers I like on this front is Chuck Yoon's papers from for YASC. And except for that, there are also more exotic schemes, if we can say that through this way, that have more complicated updates like diamonds, trapezoids, or overlapped time tiling, and several hybrid models that are combinations of them. So now we had a look about the sparse operations and a bit of timer blocking. So why, we are now going to see in the next slides, why these sparse operators, the off-the-grid operators, are entangling, are causing issues, are making, let's say, the application of temporal blocking challenging in their presence. So these operations, as we said, are not aligned in space, but they consist of a different iteration space. So our aim at the end of presenting our approach is to align them, to align those data dependencies in order not to cross different tiles in space. We're going to show in the following slides how is this problem exactly happening. So here, let's consider first of all the typical update in the green points here, the green tiles. We update at time step 0, x at equals 0 and x equals 1. And then if the sparse operator was not being at this specific place, we would be able to update point x equals 0 at time step equals 1. However, we need to think here that these diamonds are under a different loop iteration. They are in the 4 sources loop that we saw earlier, or the sparse operators, and we are able to access this position only through indirections. We are not able to merge this iteration space with the 3D iteration space, so there is no currently a schedule that helps us to be able to inspect these data dependencies already and be able, without harming the data dependencies, to update these points here. The same, of course, goes on if we continue on to the next tile, where dependencies are getting more complicated when sparse operators cross the boundary between different tiles. For example, we all know that because all these codes are huge, and not only do they have like even millions of grid points that need to be updated, all these codes, of course, are buffered. So they only keep in memory 2 or 3 time steps, like 2 or 3 clones, not exactly clones, yeah, clones in terms of space of the grid. We're not able to hold in memory all the time steps for all the space grid points. So in this case, it is clear that we are not able to proceed in time. We're not able to proceed in time when doing such an optimization like temporal blocking with sparse operators existing, because we are also in danger. We're also in danger of due to the buffered nature of these applications, to inject either earlier or later in the code with harming the data dependencies. There is no current schedule to help us do that, and for this we have to find a solution. So it's highly clear that, as you can see here, diamonds that live in the boundary between those tiles and are not updated at a schedule that is like optimized for this particular case are causing issues, and therefore harm our data dependency violations. In case we miss an injection, you see here that the red X's are in diamonds that exist in the boundary. We're having numerical inaccuracies, and of course we end up with the proceeding of time steps, and while our computation is proceeding to the future, to have all our computations being wrong, and numerically we are wrong. So we saw now what is the issue that does not allow us, or we can say that it makes challenging for us to apply temporal blocking in the presence of sparse operators. In the next slides, we are going to present a methodology. We're going to present a scheme that we built mostly over the last year in order to be able to identify, to inspect those data dependencies before the execution of our simulation code. So we built a scheme that helps us to pre-compute the source injection contribution so that we align these data dependencies to each point and thus having them at positions that are not crossing the tiles of temporal blocking updates. And of course, it was our goal, all this scheme, to have negligible cost in order our temporal blocking scheme to be efficient. And all this scheme was built using Devito's domain-specific language. We used the language of Devito, so whatever you will see in the following slides is not a compilation pass, or is not an optimization that is in the pipeline of Devito, as Fabio presented earlier, but this is rather some of the wave propagators in Devito that we just exploited Devito's domain-specific language. We exploited its power to generate C code in order to be able to overcome these limitations and generate the structure we want. Of course, this is a proof of concept we will show about wave propagators that are used in seismic imaging. However, it's going to tackle also probably other topics, other fields where we may encounter several issues. So we're now going to go through the steps of our approach here. So what we did was, in our first step, to iterate over the sources. So we iterate the sparse loop without a kernel update, and we inject this wave field just for a few time steps in a grid that is initialized to 0. So what we actually do, by making the hypothesis, of course, that our wave fields are not 0 for the first, let's say, time steps, is, as you can see in algorithm 2, just to do the source injection for a few time steps in order to be able to populate the grid at points where source injection is happening. Of course, this code was automatically generated with Devito, as we said earlier, and it's independent of the injection type. So I would like to lead you here to the subfigure A, where it looks like, it is an XY plane. It's like a Z slice of a 3D grid where we are having the presence of sources that, as you can see, are not aligned with the grid points. Of course, sources are with the blue markers here. And after executing the few time steps, we have something like in subfigure B, where the empty grid is holding values in the points that are black with the green background. So what we do here is what? We create a binary mask, a binary 3D mask that holds ones in the affected positions and zeros at the non-affected positions. Binary integer mask. And we also create another, we also construct another 3D structure that holds a unique ID for each point affected. Of course, there is high chance that the two sources inject at positions where simultaneously affect a grid point. So a grid point may get input from two sources or more. So we also construct this array holding a unique ID for each point affected, and then we do what? Then it may sound a bit weird the way I say it here, but on top of the Devito domain-specific language, we build our equations in a way to decompose our wave fields, to decompose our source data in new sources that at this time they are aligned with the source grid. So if we initially had like a number of sources, for example, 10 sources, and these sources were affecting, for example, 40 points, then instead of 10 sources, we now have 40 sources by doing something like injecting sources to new sources data. This sounds a bit weird, but well, in typical mathematics, we could just say that we decompose the effect of a wave field with specific weights to new wave fields. For example, in this particular case, we had 4 sources, and our new structure has, let's say, 3, 7, 9 sources. Some pseudocode here for this particular case. We're using this source ID to do another indirection. The source ID is the array holding the values with the unique IDs. And from this point on, we'll name our binary mask as source mask and our unique ID array as source ID. So now what we have done is that we have changed the indirection mapping of the initial sources, and we have a new one. We still use them, but now they're aligned on the point. And through this, we build we create another Z loop, still using Devito's domain-specific language, inside the kernel update. So a function here is the kernel update we saw before, the typical stencil. And the way we now inject the sources in the new Z loop is that we're using the source mask in order to inject if it is 1, or not inject if it is 0, the corresponding value of the new sources through doing a new indirection here using the source ID structure with holding the unique point values from before. So this is able at this point to align the source injection with the grid points. However, it is clear that we talk about very sparse operations. And as you saw before, like in the general case, the source mask was like extremely sparse. So it looks like a big waste of cycles at this point because we are doing a lot of zero multiplications. Here, something I forgot to mention a bit earlier is that by using this new Z loop here, we're able in some cases and some platforms to do also CMD vectorization over something that was sequential before. But let's not dive more into that. Maybe not needed enough. So in order to avoid to having all these zero multiplications that in the general case are fully redundant, we need to find a way to perform only the necessary operations by having, however, still an optimized scheme in terms of OpenMP parallelization and CMD vectorization. Here it is not shown in this algorithm here, but not before, but Devito is doing the loop blocking, usually at X and Y loops when we're talking about stencil update, space blocking as well, using collapse loops over X and Y, and doing vectorization on the Z innermost loop. So what we did here, in order to alleviate the issue that we mentioned in the previous slide, is that we aggregated the non-zero occurrences of our source mask and the source ID structure. Due to the sparsity, we're able to aggregate the non-zero occurrences for each Z column in this 3D array. And for each of these occurrences, to have the corresponding slices or layers to be able to use this new, from this point on, we'll call them sparse source ID and sparse source mask that have reduced size and are efficiently shaped compared to the previous big structures for our kernels. So the new pseudocode that you are seeing here is using the second Z innermost loop, but instead of now traversing through the whole Z dimension extent, it only traverses when needed to a dynamical bound the number of non-zero masks that you can see in subfigure here that holds only the number of iterations that are needed to perform only the necessary injections. We use these new arrays in order to be able to do in an efficient way still the source injection operation. So here is a summary of where we were in the beginning. Like in algorithm 1 that we saw earlier in our slides, we had the sources loops that was not aligned to the 3D stencil, still in the time loop. And what we managed to transform, how we managed to transform this loop is to end up having this structure here in algorithm 6, the one showed in the previous slide. You can see that instead of having this imperfect loop nest with sources, we now have only traversing over the X, Y, and Z space, having what? Having a structure that is aligned to a grid, that has the same operation count, and that is able to keep the parallelism in the X and Y dimensions, plus the CMD. I'm putting here the question mark in parentheses. Not that I'm wondering whether we may have CMD, but we're sometimes wondering maybe we can get more CMD. However, at the general case, this is not really possible. And then our next step would be to apply temporal blocking, to see how we're able to apply temporal blocking, because we are managed to overcome the issue that we had before. As you can see in the bottom right figure here, now the diamonds, instead of being at the boundary or in sparse of the grid positions, we're able to have now data dependencies that are on the point. So actually, the two arrays that each diamond had to its right and left neighbor have disappeared, or actually they have not disappeared, but now there exists only one array that is vertical down to the 2D space here, so it looks directly to the grid point. So there are no cross-style dependencies here. One thing that maybe I didn't mention before, I'm afraid I didn't mention that before, is that when I talk about tile, I'm talking about a temporal wavefront. Okay, and I'm not talking about space blocks, for example. So this is a convention that I should have mentioned earlier. I hope it's not too late. So a tile, for example, we have the green tile and the orange tile here. So while a space block is the typical space block we all know. So our proof of concept was the wavefront temporal blocking, one of the simple cases. However, we are not only limited to this. Our model is supposed to give us the capability to apply the same transformation to other temporal blocking as well. And so far, all the thing we have done is using the Devito domain-specific language. From this point on, we're not using Devito to do like loop transformations or similar things, but rather we are using an attribute, we're using a capability that Devito has, and I think Fabio mentioned towards the end of his talk, concerning also some companies that are able to manipulate the C code and do some performance tricks a lot of times. So Devito has a capability called JIT backdoor. We cannot say more about. I will not say more about that, but we're able, after the generated C code has been done, to make changes on the C code and then just in time recompile and execute to apply the operator. And also, as another grid, yes, we said that. Wavefront temporal blocking, one important thing to know is that we have a skewing factor that depends on the data dependency distances. So in the general case, the data dependency distances are defined from the order of discretization that we're using. So for this particular case here, we have the green point being updated using the orange one. So the problem of space order 4 here. And due to the buffering of the code, it substitutes the yellow point in the memory. And the subfigure A here on the right, you can see the tiles, how they're updated sequentially. And because we also mentioned that some of our models are multi-grid, and in some cases we also have cross-loop data dependencies, we're also forced to skew a bit more when we encounter this kind of dependency in order to satisfy them. So here you can see in the time axis that we actually have for time step 0. First we update, for example, a pressure field and a velocity field. The one reads from the other, and this commutation continues this way on. So, manual transformation using Devito's capabilities. Our final loop structure using the wavefront temporal blocking looks like that. For a specific time block, like we want to compute a specific number of time iterations in the future, we have for the extent of the X tile and the Y tile. Then for each time steps at this specific block, we're having OpenMP parallelism collapsing the X block and Y blocks, and then CMD vectorization in the innermost loops, and the source injection and the stencil kernel update. You can see here we have X minus time and Y minus time in both of them in order to satisfy the skewing that happens through the temporal blocking schemes, in this case the wavefront update, as we said. So at this point we have managed to create a structure, to generate to have temporal blocking that is applicable to wave propagators. We would like now to test our hypothesis, to do some experimental evaluation to see if it's worth it to apply that to our models. So Devito has quite a few models. For my work here, I used 3 of these: the isotropic acoustic, the isotropic elastic, and the anisotropic acoustic that you also saw in the previous talk, also mentioned as TTI. The isotropic acoustic, Laplacian-like low-cost, typical stencil, single-scalar partial differential equation. The isotropic elastic has a coupled system of vectorial and tensorial partial differential equations. Instead of an acoustic source, it's using an explosive source in the general case. It has more data movement. It's first order in time, not second order as the isotropic acoustic and the anisotropic acoustic are, and has these cross-loop data dependencies that we mentioned earlier in sub-figure wavefront temporal blocking update, where we need to read from 2 groups of grids. All these propagators are industrial level ones, and they also have damping fields and absorbing boundary conditions. And we run these temporal blocking schemes over those 3 wave propagators using 512 cubic grids for 512 millisecond simulation time. I'm just having here as a placeholder a picture of how TTI wave propagation looks like in anisotropic media, like the anisotropic acoustic, the velocity field after a simulation time of 512 milliseconds. So now we're going to present the results of our experimental evaluation. We actually tested our kernels on the cloud. We used Azure virtual machines. We used the Broadwell and the Skylake, whose characteristics are shown in the bottom left picture. We used GCC and ICC compilers, similar numbers for those. Here we present the results from ICC. Of course, these were all single socket experiments, no hyper-threading, thread pinning. We took care of thread pinning, OpenMP parallelism and CFD vectorization set, and also all these were done after aggressive auto-tuning in order to compare to the fairest extent possible our temporal blocking scheme with spatially blocked, highly vectorized generated C code from Devito, aggressively auto-tuned, as I said. So we tested for 3 space orders, the previous models, space order 4, 8, 12. So temporal blocking is known to deliver good performance for low orders. However, what is a low order and a medium order is a bit ambiguous, in some cases from field to field. So in space order 4, we were able, for the acoustic case, to achieve a speed up of 1.6 for acoustic case, for the anisotropic acoustic up to 1.4 plus, like it should be 1.4345 here in the Broadwell, and 1.2 and 1.3 Skylake and Broadwell respectively for the elastic model. The elastic model was more difficult because we had to skew more due to the cross-loop dependencies, as we said. So there is not much reuse. Actually, there is no much reuse compared to the other models. Reuse also decreases when we increase our discretization order or space order. We still had the 1.15, around 1.15 speed up for acoustic, and we got some for elastic on Broadwell, some for TTI on Skylake. A bit of a weird situation here. We would expect a bit more for the elastic in Skylake and for the TTI on Broadwell, but maybe we have to auto-tune a bit more, I don't know. However, it was pretty aggressive. And around as expected, almost level, almost the same performance in space order 12. That is a really high space order used in some really industrial level applications. That is also part of our future work in order to be able to improve this. I'm also having here to see how was our speed up. Was the speed up in really from a fast code? Yes, it was. I'm presenting here a Cassaware roofline model generated from Intel Parallel Studio, from Advisor specifically. where I present the speed ups we got. So this is for the Broadwell machine. I didn't have the time before to run these experiments on the Skylake as well, because the profiling is actually quite time consuming in these cases. And we present the acoustic case here. With the red color, you can see the Devito generated code, spatially blocked, highly vectorized, almost bound by the L3 bandwidth for space order 4 and 8, good reuse for space order 12. Space order 12 is the square, of course, space order 8, the circle, space order 4 is the triangle. We see here that we were able for space order 4 and space order 8 to break the L3 bandwidth and be bounded by the L2 bandwidth. So I'm just having this castle waterfall model here to show that our speed up was over a highly efficient code, and I mean a very efficient code, and we were able to really make an impact here, at least for space order 4 and space order 8. So going towards the end of the talk, just to check how much time I have. Okay, I think we're good. All here, as Fabio showed earlier to you, like a code snippet of how an acoustic wave propagator modeling is done in Devito, domain-specific language. I'm not pretending that, I'm not expecting you to look like to deep dive into this code and try to understand all the intricacies of the domain-specific language at this point. But I just wanted to point out again that I built all the inspection scheme and the alignment one using the Devito domain-specific language in order to be able to identify all these data dependencies and create a new schedule in order to be able to apply then with manual transformations the temporal blocking. So that's the only reason I'm having this codes here, these snippets here, just so that some snippets of the model a bit using the domain-specific language. So to conclude, as I said, we built a model that has negligible inspection cost in order to overcome the limitation caused by sparse operators. And we present an approach to apply temporal blocking on these stencil codes of practical application interest built on top of DSL. Our experimental evaluation showed performance gains up to 1.6 space order 4 and 1.2 on medium order 8. Well, the greatest part, almost like the vast majority, the majority of this work is adapted from work that we recently submitted, and it's also available online that you can access it on Archive. And some of our future plans in order to continue this work would be to integrate and automate all this model, possibly as a, I don't know, this is a decision we have to make, a compilation pass or at some other place in the whole Devito compilation pipeline, so that maybe the temporal blocking code generation is also being done. Would also be nice to check how it's performing on GPUs. There have been some recent works that show temporal blocking on GPUs using some more sophisticated schemes like 2.5D tiling or highly vectorized using SMTs, etc. And what would also be interested is to try to chase some performance gains for higher orders. Maybe we can check here some different platforms or many core systems in single socket, or even try some techniques like stencil retiming or stencil reordering that have proven to be efficient for this kind of codes. All this work is open source. You can access these kernels, you can access the C code. Feel free to contact us if you have any questions or you'd like to discuss more. There is a GitHub link that's actually a fork of Devito 4.2.3 that has my work on top of the master branch. And of course, the website and Slack that you saw earlier with Fabio, and where our work is supported from here. And of course, I would like to thank some collaborators, contributors throughout the work. That's Navjot from Imperial and Edward, and John Washburn from Chevron. And holding this slide here, I would also love to hear your questions and do some discussion here. Thank you very much for your attention and your patience.
Thank you, George. Very interesting stuff. Let us have some questions. Shout out if you have a question. I have a couple. Can we go back to the roof line plot?
Yes. Yes. Can you see the roof line, Istvan?
Yes.
Okay.
So basically you showed that with increasing space order, you don't really get an improvement by using tiling. And, you know, I would assume that's because the code becomes less bandwidth bound and more computationally intensive. But this seems to be showing the exact opposite. You have the space order 12 have the lowest arithmetic intensity, right?
Yeah, this case is, to be honest, I was expecting this question because this, as I said, is a cache-aware roof-line model. So it computes data movement in a bit of a different way. It's not like a conventional roof-line where we calculate the operational density and with higher space order, we're expecting to have more operational density towards the right side, towards the compute bandwidth side of a roofline plot. So, because I was expecting this question, I also have in my appendix what this particular is here about. I have a link about how the cache-aware roofline model is able to create this kind of reduced arithmetic density through the data movement, and helps us to better get a grasp of how good our application is using each specific cache level. I'm not sure if this covers your question, Istvan.
Okay, so arithmetic density does increase for higher orders, right?
Indeed, it decreases. Of course, it decreases. However, this cache-aware roofline model computes the data movement in a different way to showcase us in a better way where exactly we are banded. It's one of the latest Intel features in the Intel Advisor.
Yeah, so I guess it then, because you end up accessing the same stuff multiple times that are not in registers, you keep going to L1 and then those are counted. So
yeah, there is a part of data movements that are not taken into account when calculating the operational density, because it considers that they are already there, so they are not moved.
So did you look at, so Fabio showed these different levels of optimizations, which basically further reduce operational intensity. How cache blocking, behaves with those versions.
Sorry, how cache block? You mean temporal cache blocking or the spatial or?
So for let's say a high space order like 12, that's what one would expect, but with the naive version, which really has a high operational density, you would get very little improvement from cache blocking, and then as more aggressive optimizations are applied, you would get better and better speed up.
All these comparisons presented here are using the best performing generated code from Devito with all optimizations enabled. So I have not tested how is this model behaving with unoptimized, like in terms of less passes generated code from Devito.
Right, sure.
Istvan, very quickly, do you think it's something which is worth trying? I mean, less aggressive optimization, less aggressive flop optimization and then doing time tiling on top of that. Is that what you were asking, basically?
Yes, yes, basically. I guess it's more of a sanity check, but because I wouldn't really expect better performance. But
okay, makes sense. Yeah.
Okay, so currently, as I understand, you only do skewed tiling, but you did mention all sorts of various other methods. So I guess once you move to MPI, will you have to move to a different tiling scheme?
Oh yeah, like so far I have not touched MPI at all. If it would be placed in future work, it would be probably far from now. In general, MPI and temporal blocking are not, to the best of my knowledge, are not the easiest stuff to use together. You have to do some, if I'm not mistaken, some communication overlap over the different halos that each of the wavefront will be using. In general, it's very complicated, and to be honest, I have not searched the literature more about it at this point.
So Fabio mentioned less than ideal scaling, and I think this is something that can help further with that. So you have these really large halos, but if you start tiling, then you can combine that with latency hiding and do all your internal tiles while the halo exchange goes on for the boundary, and then you get more overlap.
To be honest, I'm not sure how that would behave in terms of performance, but in any case, what I would say for sure is that for high space order, the already limited performance from temporal blocking would increase for sure the communication overlap between MPI processes.
And I'm sure it would become insanely complicated.
But you have a point, Istvan, about so basically you would be exchanging fatter halos, right? So you can overlap more.
Yes.
Yeah. Which is what you do in OPS, by the way.
Yes, but we do not do overlap, sadly, yet.
Ah, right. Is it just because you didn't have the time to implement it, or was it for some other technical?
Yeah, we just didn't have the time. So another question, do you generate explicit SIMD code, or do you currently just rely on auto-vectorization?
The CMD code is explicitly generated. What is not generated is the loop schedule in temporal blocking. So
you use SIMD intrinsics or wrapped in C++ classes?
No, I'm just using the Devito generated CMD, Pragma OpenMP CMD vectorization.
Oh, right. Okay, so you do rely on compiler auto-vectorization.
Yes, for this Z innermost loop that we create, yes. I mean, as I said, most of this is generated using the Devito domain-specific language, except the skewing and I mean, consequently, the loop exchange of T and X of the wavefront scheme.
Sure. I assume you mostly measured all this with the Intel compiler?
So as I said here in the results, I checked both ICC and GCC. They were similar, really similar, like almost the same. And but here in this plot, you see the ICC.
All right. Okay.
I had in plan to add the GCC as well, but it was really like duplicating points at the same place.
Okay, so one of the reasons why I asked about SIMD is we have this interesting new ARM instruction set for the SV, the scale variable. I don't remember the exact words, but it's a variable vector length. That could be really interesting, and also just to see how the compiler is auto-vectorized for that. But that's completely orthogonal to what you did here.
I see.
Okay, any other questions? Okay, in that case, thank you very much, George.
Thank you very much, everybody.
Interesting talk. And we are going to take a lunch break now, and we will return at 2 in the afternoon, local time. That would be 1 in the UK. Thank you, everyone.
Thank you.
Thanks. Bye-bye.
Okay, hello everyone. Let us try and return from our lunch break. Next up, it is my pleasure to introduce Sebastian Kuckuk from the Friedrich-Alexander Universität in Erlangen-Nürnberg, who is going to tell us about ExaStencils.
Yes, thank you very much also for giving me the chance to speak about code generation. I'll just dive right in. So when we started this project, we had one main motivation, and this is in line with many of the other talks we've heard up till now. Namely, we wanted to solve PDEs. And what we quickly found out is that there's a diverse domain knowledge required to do so. And this, of course, includes the PDE to be solved necessarily, but also something like a suitable discretization. And this could be something like finite differences or volumes or elements or discontinuous discretization or something like that. Once you have a suitable discretization, you have to think about actually using a solver to solve for the system of equations that arises from the discretization. And of course, this needs to sort of be tuned to the PDE to be solved in the discretization. Once you have the numerical solver, you can think about how to actually implement that. And usually, since we want to solve large problems, this has to be some sort of parallel implementation, ideally a highly or massively parallel implementation. And what we also quickly found out is that you need all of these different layers or levels of domain knowledge, and these are usually provided by different experts. And I'm sort of sketching this in a cartoony fashion, so please try not to be offended. So for the PDE to be solved, let's say we want to ask a natural scientist, because this is the guy who wants to do the science at the end of the day, and he has the PDEs he wants to be solved to generate knowledge. But he doesn't really care about the discretization or all the other stuff. He just is interested in getting a solution. For the discretization, we could ask a mathematician or an engineer, somebody who has been working on that, and you will see sometimes these people will also be the same person. For the numerical solver, we will most likely ask a mathematician or an applied mathematician. But usually these mathematicians, they're very interested in researching different solver components, but they're not really interested in how this is implemented, especially in a highly optimized fashion. So here we would ask a computer scientist who is mainly concerned with getting scalability, getting performance, and these sorts of things. And the problem is with this diverse domain knowledge that is required that each group that I just presented usually speaks a little bit of a different language. So they have contrary goals, and they also don't really have the same concepts in common. So our research question was, can we create a tool that all of these user groups can use effectively? And better yet, can we create a tool that requires only a single expert? And this could be an expert from any of these four fields. And by that, of course, it is required that we ingrain the domain knowledge in our software. And our solution, this is no surprise since this is a DSL conference, we provide a DSL with a very high level of abstraction, and then use, building on that, code generation techniques to derive a specialized implementation for the problem at hand. I will go into the details or particulars of this DSL in a minute. But first, I want to talk a little bit about the restrictions, because this is domain specific, so there needs to be some specificity. And for our restrictions, the first thing we decided to do is restrict ourselves to a certain type of grids. And we've seen this in the talks before as well in part. And we are sort of from the fraction of structured grids, where we on the one hand target uniform grids, such as or as the most basic type of grids, but we also consider, let's say, axis-aligned grids that are non-uniform, but still have a certain structure in how the grid positions are composed, and more or less topologically structured grids with unstructured positions or random positions. And on top of that, we allow to compose these structured patches in a block structured grid to get more flexibility in our computational domain. That being said, we tried to or decided against unstructured grids because we wanted to explore how we can use these code generation techniques to apply the optimizations from literature that are, in our opinion, more plentiful for these kinds of grids, because the structure that is inherent in them can usually be exploited to gain some sort of performance. And this usually now means you have another stencil DSL, quote unquote, and you have to compete with all the other stencil DSLs that are out there, which is of course not a good idea. So we wanted to specialize that even more by restricting ourselves to a certain type of solvers. And we are talking about multi-grid solvers here, and I will give a very brief introduction. So if you're from the field, and this is just a refresher, if you're not, then don't worry, it's not that critical to understand that at this point of the talk. Multigrid itself is based on two principles. So one, you have usually rather cheap operations which smooth high frequency errors, and this could be your basic Jacobi iteration, for instance. And these are not applied very often, so just 3, 4, 5 times on average. And the second principle is that you can coarsen a lower frequency error to a coarser grid, where it can be represented again, and there it will be represented with more high frequency errors because resolution is lower. And if you combine this into an iterative scheme, you will wind up with something like this. So you start at a very fine level, you smooth a little bit, and you go down, you smooth a little bit, you go down, and so on, till you wind up with something that is very coarse, usually only a couple of unknowns per MPI rank. There you do some dedicated coarse grid solving, and then you propagate or prolongate that information you've obtained as a correction to a finer grid, do a correction, smooth again, and do this again and again until you wind up at the finest level. So if you're not familiar with these types of algorithms, the important thing is you need to be able to do more or less simple stencil operations on a hierarchy of grids, and you need to be able to map information between the different grids. This is sort of the takeaway. Okay, now I've said that we needed this information from these diverse user groups, and they don't speak the same language. So just using a single domain-specific language to cater to all of their needs is probably not going to work. So what we envisioned is a different type of workflow where we have a multi-layered domain-specific language. And to get full freedom to really express the concepts for each of these user groups, we decided to model that as an external domain-specific language. And we will see why this is a good idea in a minute when I go over these different layers. So we start on layer 1, where we could have a continuous formulation. So this is just typing out the PD in a continuous fashion. So this is very similar to the input that Devito, for instance, would be getting from one of the last talks. And in our case, this would look sort of LaTeX-like, because ideally, at least we envisioned it that way, a user could just go to his or her publication, copy paste the problem description into our DSL, and then let the generator do its thing. Okay, once we have that formulation, we can go to layer 2, where we can talk about a discretization, and I will show examples about what this looks like in a minute. And once we have the discretization, as said before, we have to sort of compose a solver to work with that discretization, which we'll then do on layer 3. Since this should be mostly used by mathematicians, we will use a MATLAB-like syntax here. And once we have the discretization and the solver composition, which sort of work from 2 different angles, we can combine that into a complete program specification on our layer 4. And while we do that, lowering to layer 4, we can also add particulars about the parallelization. We can add particulars about the data structures. We can choose SOA, AOS data structures. We can add halos and halo exchanges and communication patterns and all of these sort of things. That said, it is not really necessary to start at the highest layer. So if, let's say, you're a computer scientist and you know already what you want to implement, and you want to implement this as a set of loops over a grid, then you can go directly to layer 4 and just start there. Again, likewise, if you're a mathematician and just want to plug in for a given discretization some solver components, then you can go to layer 3 directly, just work on that, and auto-generate layer 4 and ignore layer 1, essentially. Okay, in any case, once we wind up on layer 4, we have a complete program specification, and we can then lower this into our immediate representation, where we can apply some domain-specific optimizations, which I will talk about more on a later slide. And once we refine that intermediate representation to a sufficient extent, we can then pretty print this to target code such as C++ and or CUDA, enriched with MPI and OpenMP. So let's have a look at what this actually looks like. And for this, I've chosen the community's favorite test case. So in our community, if you do a stencil DSL, you have to solve Poisson in some case. So this is what we're going to do as well. A problem description could look a little bit or something like this. So we have some unknown u, we have some right-hand side f, and on the boundaries, we have a Dirichlet boundary with some boundary function g. Now this specification is not really complete because we don't know what f and g are. So usually those will be given as well. So let's just take some random functions for that. And let's see how we can implement that on layer 1. And on layer 1, we basically do the same steps. We start with some sort of domain omega, which is our unit square. So this is just a product of intervals here. Then we have these functions that live on omega. So u would be the function living on omega. And on the boundary that we set that function to have a certain value or a certain, well, function value. And for the right-hand side f, we also define that on omega. Assign it some function, and the operator itself we specify as a separate entity, and we will see why we do that in a minute. But once we have all the functions and the operators, we can combine that into our equation. So as you can see, it looks a little bit different, but it's rather close to a technical documentation. So ideally, we would now be finished, and we would start with discretizing. Of course, in practice, it doesn't really work that way because there's still some information missing. And the way we do that is keeping an eye on this, the description here. We set up an automatic finite difference discretization, excuse me. But for that, I said before, you need certain additional information, and we provide that in the form of what we call hints. And these are hints to our compiler what to do with that stuff. And we say, okay, there's a function f and u, and we want to rename those to right-hand side in solution just to be a little bit more verbose. And we want to discretize that on a grid at the nodal position. So here you could also have the cell centers or the edges, horizontal or vertically, or stuff like that. And likewise, we specify how to discretize our operator, and this is why we need to specify this as a separate entity. And we say, okay, we want to rename that operator to Laplace, again, to be more verbose. We want to discretize that with finite differences on a given domain omega, so we could also have multiple domains, and we want to use order 2. And last but not least, we want to also discretize the equation just to have a discretized variant of that available on layer 2 to build on later on. And what this does is just generate an equation on layer 2 with a discretized operator, a discretized field, and another discretized field on the right-hand side. Okay, so this would be the automatic way. Of course, you could also say, okay, I want to do this manually because I don't know, I know better, or I want to express something that's not possible with automatic discretization or some other reason. And here we have a rather simple syntax. So for this simple Laplace stencil, this would look something like this. So we have an offset and we map that to a coefficient. And again, if you're from the field, that should look rather familiar. Okay, now that we have the discretization in the back, we can think about what to do with the solver. And again, so we can either do this automatically by providing some sort of information to the generator what we actually want to achieve. And in a more or less simple case, this would look something like this. So we want to generate a solver for some unknown in some equation. And then we can go on and parameterize that, saying, okay, I want to target residual reduction of 10 orders of magnitude. And for the smoother inside my multigrid solver, I want to have a damping factor. And I want a red-black coloring because I know this is good for convergence and parallelizability. And on a coarse grid solver, I want an automatically generated conic gradient solver. And with that, our generator will happily go on, generate a multigrid solver for that, and map that on to layer 4 later on. However, again, you could also say, okay, I want to manually implement it on layer 3. And just to give you a glimpse of what that would look like, it would look like something like this. So we have functions. And what is special to our DSL is that most of the objects of the language, such as functions and fields and operators and so on, are tied to certain levels of the multi-grid hierarchy. So this is really a critical point that we ingrained in our language. And here we can see, okay, we have some v-cycle function. This is defined on all levels but the coarsest. And later on, we have another v-cycle function, which is exclusively defined on the coarsest level. So this is sort of the stop of our recursion. Here we would then implement a coarse grid solver, which is a little more lengthy, which is why it's not here. But other than that, that is the complete multi-grid solver with one more exception, the smoother. However, you can see you have operators, you have fields, you can do assignments. So this is rather easy to understand and also easy to write. The only thing that's a little more exotic is these sort of level specifiers. Okay, so now this looks already rather complete. So why would you need a layer 4? As I said before, for data structures and communications and tuning that, of course, but also for providing a main application. So in case you only want to generate a solver and have some external software using that, that's of course not necessary, but often we have the case that you want to generate a prototype application, which is in a sense complete and autonomous. And so on layer 4, you could then implement your main application. Combine or in the same line, in such a main application, you would usually have some kind of data input output, loading some initial variables or fields, writing some results, stuff like that. Could have some visualization as well. And what this looks like is something like this. So again, rather close to your favorite high-level language. You have some sort of application, and then you read a field. Then you call your generated solver from layer 3, and then you show the image. And show image would then generate an in situ visualization, which sort of displays your result. And what you can also do on layer 4 is to a certain extent interface legacy code. So the foreign function calls or calls to functions which are outside the scope of your generated code. That's of course not that much of an issue. What's more interesting here, you could also generate interface kernels for data exchange. So you can provide the data layout to a certain extent again of your external piece of software, and we will then generate a copy in and a copy out function. And this is especially important since our generator has the capability to change the data layout, the internal data layout. So this of course would then also change these interface functions, but it's still, we still retain the freedom to change the data layout to get the ultimate performance. And as I said before, you can tune data layouts, communication patterns, overlap communication and computation, and all of that stuff. Okay, so now we have a complete application of a Poisson solver. And the next question we usually get asked is, well, but does it scale or does it run well on supercomputers? And we tried that rather early out on GeoQueen, which is now decommissioned. And we started by having a more or less moderately sized problems with about 1 million unknowns per compute core. And this is a pure MPI parallelization now. And we can see that the scaling, it's not ideal, but it's rather good. And what we see as overhead is mainly increasing communication costs and the coarse grid solver, because the coarse grid problem that we solve with that dedicated solver tends to get larger and larger if you have more processes, because as I've said before, we usually stop when we have a certain number of unknowns per core or per MPI rank. And of course, if you have more MPI ranks, your total problem size increases as well. And this not only requires then more iterations, but of course also global communication, which is required in most of these crowded subspace methods, tends to get more expensive as well if you increase the number of MPI ranks. So there are two things you can do to sort of combat that. The one is, of course, you could always run a larger problem. And the second one is you could switch to hybrid parallelization, which we did. And what you see now here is not the, so here it was the time per cycle. Here it's now the time to solution. So how much time we need to actually solve the problem. And what we see here, this little bump, this is, at least we think that due to the fact that our problem is has a different grid width in X, Y, and Z dimensions. And here we would have an equal grid width in each dimension, and again here, and here we can see that the performance is rather smooth, and here we have a little more overhead. Nevertheless, we have a rather good scalability, and in the end, we solve up to 7 times 10 to the 12 unknowns on almost 500,000 of course, which amounts to almost, I think, 1.8 million threads. Okay, so this is all nice and well, and you can solve Poisson, and you can do whatever. Well, you can do massively parallel implementations of that. So that's cool, but can you do something that's more complicated? And the next thing we went and had a look at were systems of PDEs. And as a sort of illustrative example, I just choose the steady state Stokes equations here, which you can write down as such. And now so you could discretize it with finite differences, but let's just say we want to have something different to be more illustrative, and say we want to discretize that with a finite volume discretization now. And on top of that, we want to do that on staggered grids, because then it gets more stable. It has certain properties that we want to exploit. So I just want to focus on this term right here. And if we apply standard vanilla finite volume discretization to that, that would translate to something like this. So we have a surface integral over some control volume, and this would now be, for instance, this blue one. And we have our velocity field times the surface normal and integrate that. And if we take the whole integral and sum it all up, this should be 0 for every control volume. And when we implement it on layer 2, we can again see that this is rather intuitive. So we again have an equation. We call this P equation because traditionally this is just the pressure equation. And then we map this here, and this is now done by hand, to these different integrate functions. So what we do is we take the surface integral over the whole cell and break that up into 4 integrations over a line with each of the faces of the cell. So this would be the east and the west face and the north and the south face. And we know that the normal, at least in these types of Cartesian grids, are either 1, 0, or 0, 1, plus, minus. This is why the minus is here. And then we can just say, okay, so in the one direction, this selects, in a sense, the u component of the velocity, and then the other, the v component of the velocity. Okay, so once we have that, and do that for this equation as well, which sort of looks similar, but it's more code, which is why I want to skip over that. We can go to adding a solver. And again, we can use the semantics that we've seen before. So we can generate a solver, and instead of just providing one unknown and one equation, we just now provide multiple unknowns in multiple equations. So that's not an issue. But usually you just want to tune that a little bit as well, just to get an efficient solver. So the first thing you want to do is say, okay, the standard CG is not really good as a coarse grid solver for these types of saddle point problems. So what I want to do, I want to switch that out with a bi-CG step, for instance, which we can also generate. And the second thing is, usually you don't want to have point-based smoothers here, but instead you want to do something that is called the block smoother. And what it looks like is something like this. So you iterate over all the cells. And instead of just updating or solving or smoothing one of the unknowns, you do that for a bunch of unknowns. So in practice, you, for instance, go over all the pressure points, so all these little blue dots. You choose one cell and everything that is sort of connected to that cell in a sense. So these two green velocity components, these red velocity components here. And you set up a system, a small 5x5 system to solve for those. And then you update them all at once. Of course, once you get close to the boundary, you have to adapt the system. So that's a little bit of an issue. And if you get to the corners of the boundaries, it gets even more hairy. Nevertheless, on our layer 3, you can rather easily and straightforwardly describe what you want to do by using something that we call a smoother stage. So you just say, okay, I have some sort of loop base, again, the pressure points, and I want to solve for a couple of unknowns. And our convention here with these offsets is that the cell center and the left and the lower edge have the same index. And if you want to go one up, that would be then at 1, 0. This is this guy here. And again, this would be 0, 0. And this would be at 1 to the right. So at 1, 0. So this is this guy here. And as you can see, it's now more or less easy to switch out parts of this, object, of this concept, and you can very easily experiment with different types of smoother shapes. And this is something that mathematicians, at least in our project, were very interested in, to see the effects on convergence and runtime, of course, as well, due to using different sort of shapes and overlap and stuff like that. Okay, so you can do linear systems of PDEs, that's cool. What about nonlinear systems? And now I just want to have a look at an example given by the Navier-Stokes equations. And I don't want to go into too much detail here, so I just want to focus on one thing, namely the nonlinear part, because this is what we want to specialize in our DSL as well. And what we usually have to do is find a suitable linearization for that. And one of the easiest linearizations is just saying, okay, if I have some term in a k+1 iteration, this could be now really an iteration on the solver, this could be an iteration of the solver on a specific level of the multigrid hierarchy, or a time step. So this is not really clear here, but in any case, so if I would replace one version of that U with an older version of itself, then that would be fixed, and effectively this would linearize this whole operation. And in literature, this is often called frozen coefficients, which is why we decided to directly support that as a special frozen function in our generator. So you can just right now, I have a U times a frozen U or a U times a frozen V, and of course this scales to anything else as well. And our generator internally will then figure out what needs to be buffered, what needs to be used for these kind of block smoothers on the right-hand side or on the system matrix, what is the unknown, and how to construct efficient smoothness for that. Right. So, of course, this is now getting more and more complicated and more elaborate. So now would maybe be a good time to again check, can we scale that? And we start with a classical weak scaling now on a newer Joules machine. Up to 512 nodes, which is the maximum we had access to at that point. And we can see that the scalability, the weak scalability, is rather good in 2D and 3D. The issue is with these types of problems, if you change the resolution, you change the behavior of your solver. So you might need fewer or more iterations. The linearization may be more effective or not. So this is not really a good measure. So what's of course better is to have the same problem and run it again and again by throwing just more and more resources on it. So in other words, a classical strong scaling, which we of course also did. And we can see here up to about 3K cores. This looks rather good. And afterwards it trails off a bit. However, again, so this trailing off is of course also expected to a certain extent, because our multigrid hierarchy gets flatter and flatter and flatter. The coarse grid solver needs to do more and more work, and the coarse grid solver doesn't really scale. We know that from experience, and we also expect that from the numbers. Okay, so that's also quite nice that we can do that, but can we also do advanced physical models? And here we looked at a quote-unquote legacy code from some collaboration partners, which implemented a simulation for non-Newtonian and non-isothermal fluids. And what they did was apply a finite volume discretization on a staggered grid as well. However, they used a non-uniform staggered grid, so they had a certain well, adaptivity, I would say, towards the boundaries. So they resolved that finer just to capture the details of whatever's going on in the boundaries more accurately. On that, they threw a simple algorithm, so rather standard stuff, although rather old, and they implemented that in Fortran 90 with OpenMP. And in a collaborative effort, we part by part ported this legacy application until we had a full rewrite in our domain-specific language, and by that also enabled a full generation of the whole application. So these are just some result images. But what I want to focus on for them, the benefit was they got a faster code, in some cases up to an order of magnitude. The code was more stable, as it turned out, because they had in their original code some corner cases, which basically broke the solver for certain resolutions. We didn't have that or could avoid that. The code was easier to read on the one hand because well, we had again about an order of magnitude reduction in code lines just on the layer 4 code. So that would be even less lines of code on the higher levels. But also because we have these domain-specific concepts like these integrate functions. And this was their main motivation for addressing us in the first place. They got Qt and MPI for free, which is something that they claimed could not be implemented effectively in their original code, just because it was tuned very much to a very specific OpenMP parallelization. Okay, so now I want to go a little bit into detail about how this is actually implemented. And what we implemented was a transformation-based code generation framework. So in a cartoony fashion, something like this. So we get our ExaSlang layer 1 to 4, whatever description, parse it into our generator, and then through a series of very fine-grained transformation, we wind up with some C++ and or CUDA output. So effectively, this is a source-to-source framework. And we implemented that in Scala. And just to highlight why we did that, I have this very, very simplified code example of one of these transformations. And in our framework, we aggregate transformation into what we call strategies. So a strategy is just a sequence of transformations, and it is just implemented as such. So you inherit from a default strategy, give that some name, and then you can add transformations. And then you can use Scala's pattern matching capabilities. So let's say you want to match for something that is just the negative of a constant. And once you find that, you replace it with a constant with just a negative value. So you just reduce the number of nodes in your AST. Likewise, you could say, okay, so if I have a power with any given base, which as an exponent has a 1, I just have the base. Or if I have a base and as an exponent an integer, and that integer is between 2 and 4, then I'll just replace it by a multiplication where I duplicate the base the required number of times. Of course, this could not be fine-tuned, but just to show more or less the capabilities of these sort of matches. And then you can add another transformation, let's say for statements this time, and you say, okay, I'm looking for if conditions with any sort of condition that as a true body only have a list buffer of a scope. So just a single scope as a true path. And if you see that, of course, you don't need that scope. You can remove that and return just an if condition, which directly has the true body as the true body instead of the scope. Excuse me. Okay, so this is just sort of illustrating the capabilities of Scala and why we use that. Now I said we use that to also implement automatic optimizations, and I will just briefly brush over those. So on the one hand, we have the classical loop transformations, tiling. We do support temporal tiling, although we usually don't really need it because the benefits are not really tractable for our applications. Spatial tiling, on the other hand, is of course very attractive for us. Then we have these data layout transformations, as said before, so you can switch from an array of structs to struct of arrays and back and so on and so forth. But you can also do something which is called color splitting. So if you have a red-black Gauss-Seidel, you usually want to store the red and the black point separately just to be more efficient, and we can do this automatically. We can do vectorizations, explicit vectorization. So here we actually generate intrinsics. And we have all the traditional techniques, address precalculation, constant propagation, dead code elimination, CSE, and something that what we call loop carried CSE, which from what I understand is more or less the same thing that Devito is doing, at least from the last talk. However, what we're doing is we're not buffering the entire field. We're only buffering the information that is needed. So if in X direction you want to share some CSE, some common sub-expression, then you just need a buffer of size 1. So that of course is easy, but you could also share lines or planes in the other dimensions. And the interesting part here is that you need to adapt the vectorization accordingly, because otherwise you might break that through a data dependency. And you need to factor in stuff like OpenMP, because if you partition your grid for OpenMP threads, of course, every OpenMP thread needs to have its separate buffer, and this buffer needs to be sort of pre-filled before the first actual iteration is done. However, we can do all of that in a generator, and that works rather efficiently. Okay, so this is what I wanted to talk about in terms of ExaStencils. Now I want to move on. Can we use that for other projects as well? And for that, we again chose a new application, which in our case is the simulation of ocean currents. And in terms of PDEs, this means solving the 2D shallow water equations. And a short disclaimer at this point, for that, of course, we're not using a multigrid method, but instead we're using an explicit time integration and just develop that discretization. Excuse me. Okay, so we started off by doing a first prototype with a simplified model. And again, I don't want to go into detail, but the main point here is we're using a uniform grid. So that looks a little bit like this. We're using simple finite volumes with a Lax-Friedrichs term, and we do explicit time stepping as said before. And this fits rather well to our DSL. So you can go and sit down and write that down in a short amount of time, and it works. And again, we did a preliminary scaling, this time on Pitt-Stein GPU cluster, and we can see that this scales up rather well up to 2K nodes, which of course is to be expected since there's no implicit solver involved, so that should scale really well. So of course, now in the beginning, I showed a little bit of a different image. So you might ask, what about actual geometries? Can you handle those as well? And what we do here is we actually use what is often used in the community, which is an unstructured grid as input. We take that unstructured input grid and sort of re-discretize that with very coarse mesh, Then we structurally refine that very coarse mesh. And now you can already see that this looks very much like a block structured grid because it is a block structured grid. And we still have all of these little patches which have a lot of structure, which we then later can exploit for performance. But of course, this is not really a good representation of the original grid, which is why we moved the grid positions to have a closer fit of the original geometry and coastlines. Okay, on that, we could now run our finite volume discretization, but there are certain issues, which is why we chose to switch to a higher order discretization. And in our case, this is a quadrature-feed discontinuous Galerkian discretization, which we developed together with our collaboration partners. The interesting thing here is that this discretization works on triangles, and ExaStencils doesn't really support those out of the box. So what we did was we subdivided each quad cell into 2 triangles and generate kernels for these 2 types of triangles. Right. And so now the question would be, how is that implemented? And just as a reminder, this was our original workflow. And now we replace part of that workflow with a new tool because we found out we could implement all of those concepts that are required to implement this higher order discontinuous Galerkian discretization in our DSL and in our code generator. But Scala is not really suited for that because you need a lot of symbolic computations and that's hard to do. And because there's a lot of typing involved on the DSL layer. So instead, we chose to implement a dedicated front end for our language in Python, which we call GHODDESS, which is short for Generation of Higher Order Discretizations Deployed as ExaStencils, ExaSlang specification, sorry. And within that, we implement, as said before, this discontinuous Galerkian and heavily use SymPy to do so. And due to the interest of time, I think I'll skip over the implementation and come directly to how does this compare to established code. And as a reference, we use an established software, which is called UTBest. So this is an unstructured grid simulation, and it uses quadrature in contrast to our quadrature-free approach. And we, as a test case, we use a representative geometry from the Bahamas region, and we subdivide that into 82 patches for our code. For the UTBest code, this is just one big unstructured grid, so there are no patches involved at all. And we compare then, on the one hand, the solutions, and we can see that for the surface elevation, these results are in very good agreement. So we can more or less reproduce the results of the original software, which is good. But of course, now it would be more interesting to see can we have a performance gain from that. And the answer is yes. So for order 0, this would be now a finite volume discretization. We can see that the blue line is UT best and lower is better. So we can see that the red and green lines, this is our generated code, that in most cases we're better. The difference here is the green lines represents a variant where we added a parallelization, which is not available in the original code. So if you compare the red and the blue lines, you can see for the serial version, our approach works rather well. And for parallelization, it depends. And this is, of course, also expected if you have very small fragments or very small patches. You have a lot of communication between those patches, and this inhibits getting a good performance. And this gets sort of better when you switch to a higher discretization. So this is now a linear discretization. And you can see again, blue would be the reference code, that we are faster in most cases, and the parallelization again adds a little more performance again. And if we go to an even higher discretization, we basically see the same type of effect, with one exception. For very small patches, the quadrature code is again a little bit faster. Nevertheless, overall, we get good speedups. We get a parallelization for free. We get distributed memory parallelization for free. And this, of course, is rather attractive to the users. Okay, so to conclude and wrap this all up, I have presented the ExaSlang language stack and the code generation framework below that, which allows us to do full program generation from very domain-specific representations. And we did that for a wide range of applications, from which I represented a few. And we can add automatic parallelization, such that we can scale up to millions of threads on heterogeneous architectures. We can add in all the traditional optimizations that you want. We can add in some domain-specific optimizations. And we're still, excuse me, rather well equipped to extend that for new use cases. Building on top of that, I presented the GHODDESS framework, which allows implementing novel quadrature-free discontinuous Galerkin methods applied to the shallow water equations in a very intuitive Python frontend. Unfortunately, this is the part I skipped. But if you want more insight, you can just talk to me after the talk. And from that, we can generate realistic simulations on realistic geometries, still using or exploiting the structure in the grids that we generate. And building on that, what are our next steps? Well, we want to look into adaptivity. So this mainly concerns adaptivity in the number of degrees of freedom for each triangle. We're pretty far in that respect right now. So we're based on that, we then want to do a more detailed performance analysis to see if there are bottlenecks in our generated application, and how the different parts that we generate compared with the parts of the reference code. And we want to also address some issues with load balancing that might arise either through the adaptivity itself or through the more advanced components that are required to have a realistic simulation. And what I mean by that is you, of course, need specific initial conditions, right-hand sides, and boundary conditions. And while the right-hand side and the initial conditions usually don't provide an issue for load balancing, the boundary conditions in some cases might, because the boundary conditions can get rather expensive, and that, of course, destroys your otherwise ideal load balancing. Another thing we want to look at is speeding up the code generation itself, because Python is not really the fastest language out there, and SymPy has a fair share of issues. So this combines to having rather long generation times for the very high order discretizations in Python. And of course, also the descriptions that are emitted by that and that are fed into ExaStencils get very large. So ExaStencils needs a fair share of time to process that as well. And last but not least, we want to intensify our efforts in interfacing with external software. And on the one hand, this means interfacing the generator itself. So maybe try mapping our IR to the IR of another tool. So grid tools could be a viable target for that. And also for the generated code. And here we want to use our software components in the scope of larger software frameworks. And for that, we of course need to generate more interfaces, and these need to be specialized even more to the target software we want to couple to. Okay, so this is basically all I wanted to talk about today. So with that, I'd like to thank you for your attention, and I'm happy to answer any questions that may have come up through the talk.
Thank you, Sebastian. Very interesting stuff. I again have a page of questions. Let me just start with the languages. So you have a new language, ExaSlang or slang, and with GHODDESS, as I understand, you go from Python to ExaSlang to Scala to C++.
Yes, basically.
It seems to me. Can you just discuss a bit the reasoning behind why a custom language and then why the extra Scala step and all that?
Okay, so the custom language, as said before, is due to the fact that we envisioned a very diverse group of users. So we wanted to cater to the needs of each of these user groups, and one guy wants to implement it as in sort of like this MATLAB fashion, and one and the computer scientist wants to fiddle around with the loop order, for instance. And these are concepts that don't really go well together in our opinion, which is why we wanted to separate them so that each individual can work with the concepts he is familiar with. And this is best done, in our opinion, in an external language, because then we have the freedom to really shape the language to cater to the needs. So from that, we map to Scala, which is only partially true. So we don't really map to Scala, we map to some sort of abstract representation. But this, of course, could be implemented in any other language as well. And we just chose Scala because for a code generation framework, these pattern matching capabilities have been trying to demonstrate are rather handy. And this allows us to implement these transformations that we do on the abstract syntax tree rather effectively. And for GHODDESS, again, so it would be possible to implement that in our original DSL, but having something that is a little bit more, well, let's say we have certain concepts that we cannot express in our language, but which we can express in Python. And that, in addition to the capabilities of SymPy for symbolic computations, allowed us to have a more natural workflow to implement these concepts that we require for the new application. Nevertheless, we didn't want to map from that Python module directly to our target code, because then we would have to replicate a lot of the work that has already been flowing into ExaStencils. So this is why we map to a layer 4, even if we have to bend the concepts a little bit, but we still retain the parallelization, which is more or less automatic, the mapping to GPU and stuff like that.
Okay, thank you. So with the ExaStencils, I saw that it does finite differences and finite volume, but it didn't do finite element or discontinuous Galerkin.
Right, so if you come down from layer 1, you want an automatic discretization, there's only finite differences available. If you start on layer 2, you could write down finite differences. You can write down finite volumes rather effectively with these integrate sort of statements or expressions. However, nothing stops you from implementing a finite element discretization on layer 2. There's just no real language support for that. But in the past, we have implemented for Stokes, for instance, a finite difference discretization and generated multi-grid solvers for that. That works as well. But again, there's no real language concept expressing those sort of finite element concepts. But if you can write the discretization down as a stencil, you're fine. or more stencils, depending on the order of your discretization.
Right, okay. I also had a question about this multi-block structured mesh. So how do you parallelize intra-block and inter-block? So you mentioned this 80 blocks, which is an interesting number when you want to scale. It's sort of not a lot, but also not enough in some sense for some types of parallelization.
Okay, so the grid generation, the generation of the block structured grids is sort of flexible. So you can try to provide a target number of patches that you want to wind up with. Of course, usually there's a lower bound to do that, especially maybe you can go, especially if you have something like these islands here, then this again gives you a sort of lower bound for the number of patches. But of course, you could always have more patches. That's not an issue. And to the first part of the question, these patches can now be freely distributed across MPI rings. And we then generate specialized communication for these or for the patches within one MPI ring and across MPI rings. And in the one case, that would be your classic message parsing communication. So just packing that into a buffer using an MPI data type. And in the other case, this would be a simple copy operation. So this could be a mem copy or a loop which copies elements, stuff like that.
Okay, interesting. Fabio, you had some question?
Yeah, thanks for the talk. It was really nice. Yeah, mine are just curiosities. So first of all, is this open source? And if yes, where?
So ExaStencils is open source. I can send you the link via the chat after the talk.
Yeah, that'd be cute. Yeah, thanks.
Although I think it's not the most recent version. GHODDESS itself is not open source yet, but it will be in the future.
Yeah, that's a pity, but yeah, I get that. Yeah, but just one comment. So yeah, your loop carried CSE is exactly what we have in the Vita. We have the same sort of flexibility you were talking about during your talk. And another question is, so how do you do boundary conditions which are not non-Dirichlet like boundary conditions? So if you have something fancier, like you want to run, you want to execute some custom stencils around the side of the plane or free surfaces, stuff like that.
Okay, free surfaces could be a little more complicated. Maybe I can comment on what we do in general. So there's a hierarchy more or less of concepts you can use. You can either provide something like a Dirichlet boundary condition as I've shown, and that will generate kernels that will reconstruct values in the ghost layer to set the boundary condition. Such that at the inner part of the patch, you don't have to modify the communication at all, which we need to exploit the structure. Via certain compiler flags, you could also change the order of that reconstruction. So usually this is just a simple linear extrapolation, but of course you could also do something more higher order. If you want different boundary conditions, then it depends on what you want. So if you want something like a Neumann boundary condition, then we have built-in support for that as well. So you just say, okay, on the boundary I have Neumann, and then we generate kernels doing that. If you want something more, let's say, exotic or specialized, then we have loop structures which provide you the opportunity to iterate over boundaries and set values either in the ghost layer or shortly before the ghost layer with whatever specialized kernel you want to have.
Okay, yeah.
So if you can express your boundary condition as a stencil code, you're basically not running into any issues.
Yeah, makes sense. How many people are working on this, by the way, out of curiosity?
It depends. So it varies a little bit. So I think right now it should be about 3 or 4, plus some students.
Okay. Thanks. Thanks a lot.
Thank you.
A quick question. So you have this shallow water code. how much shorter did it become compared to the original UT best? If
that's a good question. So the thing is, in terms of Python, so the Python front end compared to the original code, we didn't do that comparison, to be honest. So I can't really comment on that, but I would expect it to be about in the same ballpark. So I don't think there's too much difference there, but of course we provide more parallelization capabilities, more optimizations, and so on and so on. For the ExaSlang code compared to the legacy code or the reference code, again, we didn't do that comparison, but I would expect it again to be rather similar. If you select the actual parts of the reference code that you want to do computations with, because of course they have different modules doing different things, and if you just take sort of the critical path through the program and extract that, then it should be about the same order and lines of code. However, they are doing quadrature, so for every integration of a triangles or edges they have just a more or less deep loop nest. Whereas we have a quadrature-free approach, so we can't really do a loop over something. So we have to sort of unroll, in a sense, these loops, which is why these expressions tend to grow larger and larger, especially if you're doing higher order. So in, let's say, characters, I think for the higher orders, we will have a lot more compared to reference code again. But since this is generated by a front end, this is not really our main concern.
Great, thank you.
Maybe a quick question, if I may. How many people are present on site?
The site? You mean the Zoom call?
No,
in person. Varies between 10 and 20.
Oh, okay, cool.
Yeah, COVID restrictions.
Yeah.
Okay, thank you, Sebastian. If there are no further questions, then we are going to move on to David Lusher, who, well, formerly of University of Southampton, where he developed this or did this work, and recently moved to the Okinawa Institute of Science and Technology in Japan.
Hi, can you hear me?
Yes.
Okay, just share my screen. Okay, can you see the slides?
Yes.
Okay, great. Yeah. Okay, so yeah, hi everyone, I'm David. All this work was done during my PhD project at the University of Southampton. Today we'll be talking to you about OpenSBLI, which is our code generation system for computational fluid dynamics. And we've had a lot of talks so far that have focused a lot on the design of the domain-specific languages and a lot of the low-level constructs. I won't be talking too much about that. I'll be talking a lot more about how we actually use a DSL as kind of end users. And so I'll be showing a lot of applications of how we actually use DSLs to simulate problems within fluid dynamics. We had a...
sorry, David, to interrupt. The screen right now is blank.
Oh, it's blank? Oh.
Now it's...
Can you see it now?
Yes.
Okay, I'll keep it in this view then. So yeah, this work was done with Satya Jami and my advisor, Neil Sandham. So we had a version of OpenSBLI before I joined, which was a kind of proof of concept of the code generation for fluid dynamics. This was a very basic version. And then when I started my PhD, we started a new version together, and this is the new version that everyone uses now. So for an overview of the talk, our domain is computational fluid dynamics. So I'll give a quick introduction of what CFD is, the governing equations that we're dealing with, and some of the subtleties of compressible flow. We have to deal with shock waves, and we need special numerical schemes to capture these shock waves. And then the main part of the talk will be discussing OpenSBLI. So this is a compressible Navier-Stokes solver, which uses the OPS DSL to do the parallelization step. Like we've seen before with codes like Devito, we use a Python SymP code generation to generate RC code. And I'll give a bit of information about the performance and scaling. And then I'll finish the talk with some applications of the actual physics that we work on and some of the other applications that our users use the code for. So computational fluid dynamics is the numerical study of the conservation laws that govern fluid motion. So by fluid, I mean by gases and liquids. CFD has applications, wide applications throughout science and engineering. For example, in aerospace applications, high-speed aircraft, astronautics, also automotive naval applications, and then also kind of biomedical applications. So if you are interested in modeling the respiratory system or blood circulation, for example, this would also be within the domain of fluid dynamics. These two examples on the right are just some visualizations of the kind of flows that we deal with. The one on the top is a periodic box of turbulence. This is a Taylor-Green vortex case. The quantities you're looking at here are Q criterion surfaces. So these are surfaces of vorticity. So each of these filaments here are regions of rotating fluid. And in CFD, you have a very wide range of time and length scales that must be captured depending on the problem. The picture on the bottom here is a 2D slice of a 3-dimensional simulation. So in this case, this is a supersonic flow through an enclosed duct. So this is a kind of a rectangular duct where you have enclosed walls all the way around the duct. And then on the wall on the bottom and the top here, you have a boundary layer flow that develops, and then this transitions to turbulence. So you can see there's a large range of scales involved, and we have to try and capture these within our simulation. Within fluid dynamics, there are various levels of accuracy to cost trade-offs that you can do. So if you're working in a kind of industrial commercial code, you may be doing like a Reynolds average Navier-Stokes solver where you're solving averaged equations, which are very cheap to solve, but they have lower accuracy. Where you don't actually solve the explicit turbulence itself, but that will be added on later on as a modeling step. The next step would be something like a large eddy simulation, where you choose to simulate the larger structures within the flow, but then after a certain step, you'll have a cutoff point, and then all of the smaller scales in the flow are modeled by some kind of subgrid model. In Southampton, what we do is direct numerical simulation, which is the most expensive way of doing it, and this is where you don't have any kind of modeling tricks. You're solving the governing equations directly with finite difference methods. So to give you an idea, some of the kind of cutting edge simulations of DNS flows would be on the order of about 5 to 10 billion grid points. So these are huge simulations and can need tens or hundreds of thousands of computational cores. So the challenge for us really is being able to be able to use these machines efficiently and target the kind of simulations that we're interested in. And in Southampton, we work a lot on scientific codes, but our background is not in computational science. So we are looking for ways where we can exploit this new hardware while still being able to concentrate on the kind of numerical methods and physics that we're used to doing. So the equations that we deal with typically are the compressible Navier-Stokes equations, which are shown in the bottom here. OpenSBLI is not limited to just doing Navier-Stokes equations, but this tends to be what we're using. So this is the Navier-Stokes equations in index notations or compact notation, where you would expand over these indices depending on the number of dimensions you have. So there are 5 equations. You have conservation of mass, 3 equations for your conservation of momentum in 3 dimensions, and then a conservation of energy as well. Within this, you also have additional relations that you have to solve. So for example, P for pressure, you would have an equation of state depending on the type of gas you're dealing with. You also have relations for the viscous stress tensor and the heat flux terms as well. So although these equations look quite compact in this form, if you actually expand them out in 3 dimensions with all of the extra relations, you'll get several pages of equations that you're having to solve. And if you're also solving this in curvilinear general 3D coordinates, where you've got curved complex meshes, then you also have to do coordinate transformations, which makes it even more difficult. Within fluid dynamics, you can also make the distinction between incompressible and compressible flow. So incompressible would be applied to low speed flows. So for example, if you're doing CFD of like a road car or aerodynamics of a cyclist or something at low speed, you can make an incompressible assumption. So this is where you assume that your density rho is constant everywhere, and that leads to significant simplifications that you can do. As you get to higher and higher Mach numbers, you can no longer make that approximation, and you start getting variable density where you get regions of compression and expansion. And if your Mach number goes towards the speed of sound, Mach 1 and beyond, so for supersonic and hypersonic flows, then the nonlinearities in these equations leads to the formation of shock waves, which are discontinuities in the flow. So these are an abrupt change in your field variable. So for example, you would have a kind of a step function in your pressure and your density. And these are very difficult for regular numerical schemes to deal with. Just to illustrate this, I'll show you, this is the Invisit-Burgess equation. So this is a simple 1D conservation law that can develop a shock wave. The initial condition in this case is just a Gaussian in the black line at t equals 0. And then if you step this equation forward in time, the profile steepens and you get this discontinuous jump, which is a shock wave. The one on the bottom is how it should look when you actually have a special shock capturing scheme. Whereas if you try to apply just a regular finite difference central difference, you get this result here where essentially your finite difference stencil was trying to average from very high values up here and the very low values down here, and you get these very large spurious oscillations which completely kill your simulation. So we have to, for compressible flows like we deal with, we have to put a lot more effort into the numerical methods to actually resolve these shock waves or capture these shock waves very cleanly. I won't go into details in all the numerical methods that we have, but I'll just highlight how the ones that we use tend to work for this shock capturing. We use a family of weighted or targeted, essentially non-oscillatory schemes. So these are called Weno or Tino schemes. These are high-order Godunov type methods, where the aim is to provide a derivative of your flux Fi, where Fi would be one of the terms in the governing equations. So this is all a stencil-based code. So at each time we're trying to find values of derivatives at a generic grid point I. And the way we do this for the shock capturing schemes is to take a half node reconstruction at I plus 1/2 and another one at I minus 1/2. And then we just subtract the difference off, and that gives you the value of your flux at your ith grid point. These are typically 5th to 9th order in space, so these are quite high order schemes and they're very expensive compared to standard central differencing. The way these work is that if for your full numerical stencil may range from I minus 2 to I plus 3, but within that, that's composed of a number of smaller, what we call candidate stencils. So this S0, S1, S2, S3. And the way this works is that we want to avoid differencing over a discontinuity. So this works by taking a flux contribution F hat here over each of these individual stencils. And then we compute a nonlinear weight called omega, which is comprised of various terms. And this depends on which formulation you're using. There are literally hundreds of these that you can choose from. But the main point is that we compute this term beta, which is just a polynomial in your flow variables on each of these stencils. And that gives you a measure of the smoothness of your flow. So if you have a discontinuity present in this side of the stencil, then this S2 candidate stencil would be discarded completely and it wouldn't contribute to your flux reconstruction. So by doing that, you avoid differencing over shock waves and you get a non-oscillatory solution. There are other steps that I've omitted here as well. We also perform this in characteristic space. So there's a matrix vector multiplication to transform it from physical space into characteristic waves. And then we perform the reconstruction and then transform it back again into physical space. While these shock capturing schemes work very well for capturing shock waves, they have the detrimental effect of being overly dissipative for turbulence. So generally we have to use these Tino methods, which are low dissipated versions, which retain the shock capturing, but allow us to still simulate compressible turbulence. And there's various different methods you can do for this. So in summary, for the numerical methods, OpenSBLI is an explicit finite difference code. Everything is stencil based on structured meshes. We've got a selection of different finite difference shock capturing schemes that you can use depending on the type of case. We can generate any order within the code from kind of 3rd to 9th is typically what's used, but there's no actual limit on that. Importantly, we also have support for full 3D curvilinear coordinate transformations. So you can transform the governing equations into curvilinear space and then deal with curved complex meshes. Our viscous, metric, and heat flux terms are just solved by ordinary 4th order central differencing. But again, you have control over what order central differencing you use. And then at domain boundaries, we also switch to one-sided boundary closures, which are also high order to maintain the same order throughout the whole domain. Time stepping is just done by a 3rd or 4th order Runge-Kutta, also explicit, and these are low storage methods to try and reduce our memory usage. So moving on to the code. So OpenSBLI is a code that I've worked on for a number of years now. I'm the sole developer of this code for the last couple of years. So I'm going to talk about how it works in terms of the code generation, and then how we couple that to the OPS domain-specific language to be able to run CFD cases on emerging architectures. So a lot of these arguments have been said in previous talks, but I'll just go over a couple of them again. Scientific codes can be very difficult to maintain. This is, I think, very true for academia, especially because compared to industry, where you have the kind of funds where you can hire dedicated software engineers, in academia, codes are typically written by PhD students, postdocs, and it's kind of a side project that they do separate to the kind of their actual research question. And we often have codes. So in Southampton, we have a code called SBLI, which is a Fortran code, which has been in use for about 20-25 years now. And that's a CPU-only MPI code. So if you wanted to take a code like that and then run it on GPUs, it's very difficult to port that to CUDA, and it's a very time-consuming process that we want to try and avoid. In recent years, there are now very large supercomputers which have a large number of GPUs. For example, Summit at Oak Ridge has over 27,000 V100 GPUs. So there's a huge amount of compute capability available to us now. But as end users, we want to know how we can actually use this effectively. And that's where domain-specific languages come in. So we use domain-specific languages in terms of a separation of concerns. And so this is a way of separating the parallel programming implementation from the actual physics and numerical modeling. The benefits of this, it just takes up all of the time consumption that would have been otherwise, that could be used better in our purposes for actually simulating the physics. And we're able to benefit from hardware-specific knowledge from people like Istvan and Gihan, who write these domain-specific languages, who have a lot of knowledge about the architectures and how to get the best performance out of them. Because this is typically not something that's taught within the kind of physics and engineering education system. So OpenSBLI is written in Python. It's a code generation system that was developed at the University of Southampton by myself and Jami. It's very similar to kind of the previous talks we had today on, for example, Devito, where we specify our equations to solve in a high-level Python script, and then we use SIMPy to perform symbolic manipulations of these equations, and essentially use it to generate a complete CFD code. So although there are similarities to systems like Devito, in that we use SIMPy to perform symbolic algebra, to perform symbolic manipulation. OpenSBLI can be considered a kind of a pre-processing step. This is the workflow that we use. So all of my work is really focused in the first step here, where OpenSBLI is used in Python to generate an OPS-C code. Once you have the OPS-C code, you can then take that off to your cluster, and then you'll compile it on your cluster. So whereas things like Devito also act as a compiler, where they're doing loop optimizations, and other codes like PyFR, where they'll be using MPI for Pi to run on the compute nodes with Python itself. OpenSBLI is really just a preprocessor to get an OPS-C code. So once the code has been generated, OpenSBLI's job is done at that point, and then you're just on your supercomputer with OPS to actually run the simulation. By using this OPS DSL, we're able to generate a single source code, and then from that single source code, there's a source-to-source translation step, which will generate MPI, OpenMP, CUDA, OpenACC, and OpenCL code for us. And then depending on which architecture you're running on, you'll pick one of the computational backends, and then you can run on that architecture. So this is how OpenSBLI is structured. So starting at the top here, these are the main features of OpenSBLI. So each of these red boxes are classes that exist within OpenSBLI. So as a user, you have a high-level problem script. This will typically be about 100 lines of Python code, depending on the complexity of the problem. And so you specify the equations that you want to solve. You pick the boundary conditions you want. You set your I/O options. All of these choices get set on what we call the simulation block. The simulation block is kind of a central construct which links everything together. So if you're running a single block simulation, you'll have one of these, whereas if you're doing a multi-block simulation, you'll have multiple of these. Users will specify the schemes they want, the order of the schemes, and then once that's all set on the block, they call this discretize routine. And what this discretize routine does is that it loops through all of the equations and then finds the schemes which they should be discretized with, and then it performs a discretization procedure symbolically. So there's no actual computation being done at this stage. We're just generating symbolic representations of the analytic derivatives that the user has specified. All of these discrete representations go into what we call kernels. So a kernel is kind of a container for a certain computation. So if you have a derivative that will have its own, it will be a kernel for that derivative. And then the kernel contains all of the information required to compute that, to perform that computation. And I'll show you what these look like in a minute. And an important part to emphasize on this is that the entire code generation procedure is separate to the parallel implementation. So if in 5 to 10 years there is a new parallel programming paradigm that people are using, we wouldn't be changing anything within our actual code generation system itself. It would just be a case of adding an extra backend to the OPS library, and then we would be able to target that new hardware without having to change our existing numerical methods and so on. So once the system has discretized all of these equations and turned them into a big list of computational kernels, we have a class called algorithm, and this is basically just sorting the kernels into the order that they should appear in the simulation code. So the algorithm class just does kind of very simple things that you would do. It declares constants at the start of the simulation code. It would initialize your grid. It would compute your grid equations. It would compute metric terms, and then it would have your time loop where it would put all of the spatial kernels into the time loop. And then at the end of the program, you would have calls to the OPS library to do your input output to actually get information, get the data out of the simulation. And then the final step is the OPSC class. So this is the actual code generation part. This is the actual code writing part. So everything in the first box is actually generating the code symbolically. Everything's done within this SymPy symbolic library. And then when we get to OPSC, the OPSC class loops through the algorithm, finds all of the kernels, and then converts them into C code. So this entire process is quite quick. It tends to take about 30 seconds on a laptop to generate an entire code. It's important to note also that this code generation isn't required to use the OPS library. We just do it as a way of not having to write the OPS code ourselves. So OpenSBLI is a kind of a bookkeeping type approach where it keeps track of all the data access, the input output arrays and everything, and how the equations will be formed. But it's not actually doing any computation. So I mentioned that all of the computations get turned into OpenSBLI kernels. So these are just Python classes which allow us to store some attributes and have methods to get information out of for whatever the computation is. So in the example here, the user is just creating a kernel by passing a simulation block, the name of the computation, which in this case is a kernel to do a boundary condition. The kernel also controls the evaluation range. So this would be your range in ijk to actually loop over. You also have control of, say, the halo values and the number of halo points required to implement this boundary condition. And then you have a kernel to add equation where you just add a list of symbolic expressions, and these are the equations that would be written out into the C code at code generation time. So these are the main things that the kernel holds: the symbolic equations, halos, range of evaluation. it has to keep track of the input-output arrays for the OPS parallel loop, and then also importantly the relative data access. So if you're taking for example, a fourth-order derivative of a pressure term, you would need to access that array at I-2, I-1, I+1, and I+2. So we need to tell OPS this is the relative data access that's required at each point to be able to compute this derivative. So all of this stuff you could write by hand in OPS, but it gets very time consuming as you get to more and more complex problems, whereas OpenSBLI automates this entire process for us. And then once you get to the OPSC code writer part, this is where OPSC basically just accesses each of these kernels, and it can find all of this information. And then it populates the function arguments required for the OPS API calls. And then again, the algorithm controls where these API calls appear in your actual C code. So internally, we make a lot of use of SymPy and its symbolic algebra library. So this is a symbolic algebra engine. SymPy has a number of classes. For example, here, symbol and indexed are two examples. And these are objects that you can perform algebraic manipulations on, and they follow all the kind of standard laws of mathematics, of associativity, and so on. We have our own data types that are derived from these, so we retain all the functionality within these classes, and then we add some extra methods on top of those, which are useful for creating a CFD code for our own purposes. And importantly, having these multiple data types allows us to distinguish between terms in the symbolic equations. So if we have an equation with different derivatives, we need to be able to identify what is an actual array that should be stored globally in 3D, what should be computed locally, what is a global constant, what are spatial coordinates, for example. And so there's a few examples here. So for constant values like our Reynolds number, Prandtl number, Mach number, these would be a constant object, which are derived from symbol in SymPy. And these would be defined by OPS globally at the start of the program. Then we have spatial coordinates. This would be your X, Y, Z coordinates. These were a type coordinate object. So then when we have a derivative object, we can find out that the derivative is with respect to one of these coordinates, and then we can check the direction. And then we know which of these indices to actually increment to build up your finite difference approximation. And then we also have, for example, global arrays. So rho would be your density array, which is a 3D array in I, J, and K. And in OpenSBLI, these are called data sets based on the indexed class in SymPy. So these are similar to the previous symbols, except that they actually accept an IJK index, which you can increment. And that is what gets transformed into the relative data access that you see in the actual C code. Within SymPy, there is a C code writer. So for each of these terms, you can just do a .c code, and it gives you a C code representation of those. So at the OPSC code writing class, we basically just loop through all of the equations, all of the terms, and then we get the corresponding C representation of these terms. And then we use that in our OPSC class in conjunction with some string templates, which are basically just the calls to the OPS API for a parallel loop, or to declare a constant, or to do a reduction, for example. And then the OPSC, depending on the information within a kernel, the OPSC code writer will just populate these string templates for the arguments required to do that computation. There's a lot of other things we can use internally in SymPy to make our life a bit easier. For example, there is a piecewise function in SymPy, and this is a way of generating kind of chains of Boolean logic. So if you've got a lot of equalities where you want to set certain values depending on, for example, a spatial coordinate, this would be very useful for imposing a shockwave or something on a boundary condition. You may have a spatial dependence on your profile that you want to initialize your domain with. So you can use this piecewise function in SymPy. And then when it gets to code generation time, these piecewise functions are automatically generated into if-else statements within C. So then they evaluate these Boolean logic, these change of Boolean logic, which is very useful for us. We also have, because it's a symbolic algebra engine, we can also perform simplifications of the expressions that we're using. So a few examples would be simplify or factor, or we can apply like a Horner algorithm to reduce the number of powers that are computed. They also have a count ops function, which is a count operation function. So what we can do is we can loop over every equation that's in the simulation code, for example, calculate the count ops, and that will give you the number of operations required to compute that expression. Then you can do a simplifier or a factor, and then do count ops again. And if the number of operations is reduced due to the simplification, then you can use the simplified version rather than the regular one. So there's a lot of power of the symbolic engine that we can exploit. So this is what the code actually looks like as a user. This is a cut down version of the problem script. Typically, these are about 100 lines of code, depending on the complexity of the problem, but I've cut it down to 18 lines here just to show you the main parts. So in the first line, they're just specifying the number of dimensions of the problem. So depending on the dimensions they specify here, the equations will be expanded based on those dimensions. We specify equations, I think, similar to the Devito using the equality class in SymPy. So the notation here is just EQ left-hand side, comma, right-hand side is equal to 0. So this is defining your mass, momentum, and energy equations that I showed earlier on in the talk. And then we can also do substitutions for things like your viscous stress tensor and your heat flux terms here. And we also have the option of passing the numerical scheme to compute different derivatives with. So for the Navier-Stokes, for our convective terms, we would want to use shock capturing schemes, whereas for our viscous diffusive terms, we would use central differencing. So we need to be able to differentiate between terms that are required, that should be computed with the Tino scheme, and terms that should be computed with the central scheme. By default, if you just call a derivative without passing an argument, it will default to a central derivative. But you can change this scheme to Tino, Wino, or central. And then each of these derivatives will be discretized differently depending on that choice. So these equations are passed and then expanded over the indices, and then you have symbolic equations. The user would then specify the actual order of the scheme that they want to use. So in this example, they're using a Tino scheme, an LLF Tino scheme. So LLF stands for local Lax-Friedrichs. So this is a flux splitting method we use for the shock capturing. You pass the order, and then we use a row averaging to do this, the characteristic decomposition that I mentioned. And then you also have central schemes and then your time scheme here. So if you change your central scheme from 4 to 10 here and then regenerate the code, then you'll have a 10th order approximation for your central derivatives, and same for the shock capturing schemes. So as a user, you have quite a lot of control from quite a simple high level interface. And then here we have selection of a boundary condition. So in this example, they're asking for an isothermal wall. So this is a constant temperature, no slip wall. We have a number of different boundary condition classes that they can call within the code. And then you just specify the direction of the domain, the side of the domain you want to apply these boundary conditions, and then some equations that would be set. So in this example, I haven't shown the equations, but this would be setting an energy based on a constant temperature. And then at the end, you just call your algorithm and then the OPSC code writer. So this whole process takes less than a minute really to generate a code. The DSL that we use is the OPS library. So Gihan went through this yesterday, so I'm not going to spend a great deal of time on it. But just to show you, this is the kind of code that gets generated by OpenSBLI. The second picture here is a bit outdated. Some of these access codes are actually removed in a recent version of OPS. But you can see that we're calling an OPS par loop, where we're passing some function, which in this instance is called kernel 12, which is this function that's defined here. This is performing a central derivative of pressure into U with respect to X. And then you have your input and output arrays. So all of this stuff is handled by the kernel. You would otherwise have to write this manually by hand, which we want to avoid having to do. And at the top, we're specifying the grid range to perform this calculation over. So in this example, this is 0 to nx, 0 to ny, and 0 to nz, which is the entire 3D domain. And then on the bottom one, you have the actual body of the function, where you're just computing a 4th order central derivative, reading in this quantity work 35, indexing it in the x direction at 4 different grid points, and then assigning that to a different array. I won't speak too much on the scaling, because I think Gihan went through that a lot in the talk yesterday, and there's some references on the next slide. But one thing to highlight is that we get different scaling for our different schemes. So this is weak scaling and strong scaling for 2 different schemes within the code. The blue line is the standard central difference, whereas the red code is our is our high order shock capturing methods. Typically weak scaling on GPUs is pretty good, where we find that we are limited in GPUs in terms of the amount of memory that you have per card, and this really limits the amount of computation, the amount of problem size we can actually fit per GPU. But you can see that for whereas the central difference has maybe 7 to 8 operations to compute a finite difference stencil, the shock capturing scheme has thousands of operations to perform at each grid point. And so you get much better weak and strong scaling for the shock capturing schemes. Some of the limiting factors we've noticed with the GPUs that makes it difficult to get maybe more optimal strong scaling is that the MPI exchange time communicating between the GPUs is one of those factors. So I think ideally we would have more memory per GPU and then be able to cut down the number of GPUs that we have to use. We have a number of low storage optimizations that can help with this, where we store fewer global arrays, and then that allows us to fit a larger mesh size on a smaller number of GPUs than we would have to otherwise. Also, yeah, so this was also mentioned by Gihan yesterday, but just to give you, these are some references that discuss the performance of OPS. Some of these in the context of OpenSBLI. The first paper, they showed that each of the computational backends in OPS could generate automatic parallel code that was within plus or minus 10% of handwritten versions for the same backend. The second paper here from Jami was also based on doing low memory intensity algorithms and exploiting our code generation. So basically, for a CFD code, the standard method of working is that you would compute all of your derivatives one by one, store them to global work arrays in global memory. And then when you actually form the right-hand side to do the time update, you would read those values back in. We found it's a lot quicker if you just get rid of that step completely, and instead you just have a big kernel where you compute these derivatives once at a local grid point, use the value where it's required, and you skip that step of reading and writing to the memory. The last paper was also a comparison of OpenSBLI to our legacy Fortran code, which was, and OpenSBLI was around 30% faster on the same architecture. And if you use some of these low memory intensity algorithms, you could get up to kind of 2 times speed up compared to the old version. So the main point here is that by doing this automatic parallelization, you're not actually losing anything performance-wise, and there are actually gains that you can acquire. So that's kind of an overview of the code. Now I just want to give a few examples of the kind of physics that we deal with, and just to show you what can be done with the domain-specific language. So the area that I work in is shockwave boundary layer interactions. So this is a phenomenon that appears very widely in supersonic and hypersonic flows. So this is a gas flow that's moving from left to right over some solid surface wall. Close to the wall, you have a region called a boundary layer. So this is slow-moving fluid. And then you have an instant shockwave that's coming in and impinging on this boundary layer. So this shockwave could be created by, for example, a fin or something on an aircraft that causes a flow deflection. And then this shockwave impinges on a boundary layer on another surface of the aircraft. This shockwave causes a thickening of the boundary layer. And if your shock is sufficiently strong, you can actually cause flow separation. So your flow separates from the wall, and you get this region called a separation bubble, where your main flow is still moving left to right, but the flow within the near wall region is traveling back upstream. The curvature of the boundary layer also causes a series of compression waves that coalesce into a reflected shock. So there's a lot of interesting physics that goes on in these cases. This was the first case I worked on during my PhD. This is a 2D laminar shockwave boundary layer interaction. So this was the first test of whether the code was actually working to do the kind of problems we want to look at. So you're looking at pressure contours and velocity contours here. And you can see that there is an oblique shockwave that causes this separation bubble in the bottom. And then this was used as a validation compared to a previous reference result, and that we can see that we're matching very well the wall pressure and the skin friction coefficient. I mentioned a lot the term separation bubble. So the separation bubble is essentially defined as the distance between the 0 crossings of the skin friction curve. So we're interested in this length here. We could also do transitional problems. So this is a transitional shock boundary layer interaction. So a lot of fluid mechanics is understanding the transition from a kind of smooth laminar state that you can see in the bottom left corner here to this chaotic turbulent state where there's a lot of mixing and variation of scales. So this is a 3D simulation of an oblique shock impinging on a boundary layer, and we add a small amplitude perturbation in the free stream, so it's a kind of an acoustic source, some kind of disturbance in the acoustic field. This seeds disturbance waves in the boundary layer itself, and then as they pass through the separation bubble, they get amplified and they undergo a nonlinear breakdown to turbulence. So on the right here, we're plotting, again, Q criterion surfaces. So these are vortical structures of rotating fluid. And so we're able to study the transition mechanism using this code with the DSL. Shockwave boundary layer interactions are found in many applications, especially in aerospace applications. But typically they're done in a setting where you have a periodic span. So your boundary condition here and here is a periodic, so it's in an infinite span assumption. But this is not actually very realistic for most cases. So in the bottom here, we have engine inlets on Concorde, a supersonic airliner, and you can quite clearly see that the span here is not infinitely wide. There are sidewalls. So a lot of my PhD focused on three-dimensional effects for confined shockwave boundary layer interactions with simulations like this, where we have shocks not only impinging on the bottom wall, but we also have a swept shock interaction on the sidewall. And so we can look at flow physics that just you wouldn't be able to see in a span periodic simulation. And these are a lot more expensive, and actually using domain-specific languages allows us to tackle these kind of problems. The one on top is a diagram of a scramjet. So this would be a hypersonic vehicle where you get these oblique shock reflections, and this is called a shock train, where you get multiple shock reflections one after the other. And we have some other students in Southampton that are working on these kind of flows. Quite quickly, these are some results from my PhD and this paper that I published. So this is the kind of domain. So it's a rectangular domain, no slip walls all the way around. You then have an angled shock generator, which causes an oblique shock wave, and this reflects. These were up to about 500 million grid points, so they're quite reasonable sized simulations. And you can see that we get these flow features, these conical shock waves that you wouldn't be able to predict at all in a span periodic simulation. These are a few more flow visualizations for these cases. So this is a half cutout of the duct where you're seeing a plane of density for the shock boundary layer interaction, and then the dark blue regions are regions of flow separation. So again, as well as the central separation that we would have in an infinite span periodic case, we also get these large flow separations on the sidewalls of the domain and in the corner. And this is just a phenomenon that you wouldn't be able to reproduce in span periodic cases. And you can also do kind of streamline analysis as well, where you plot streamlines. So this plot here is a top-down view of this one. So this dark blue region in the separation bubble is what you're seeing here. And you can see that there is an ejection of the flow from the corner region into this separation bubble that spirals into a focus on either side. And then you can detect the saddle and focus points and then characterize some of these flows in terms of the streamline topology. So the cases that I showed before, these were curvilinear, but the actual deformation of the mesh was very low. So these cases recently I've been working on are for cases where we have considerable mesh deformation. And these are more challenging because as you add curvilinear terms, you get a mesh discretization effect as well, and this can affect the stability of your numerical methods. So to get a lot of these cases working, I've been having to add some kind of nonlinear filtering methods to improve the numerical stability for these cases. The one in the top is an example of a supersonic flow past a cylinder. So when you have a blunt object like a cylinder in a supersonic flow, so this is at Mach 2, so these are Mach contours. This is high speed flow here and then low speed in front of and behind the cylinder. In these examples, you get what's called a bow shock. So this would be kind of representative of like a re-entry capsule coming back into the Earth's atmosphere, and you get this this wide bow shock in front, and you get intense heating. So these are quite challenging cases for a structured mesh code. The one on the bottom is also one of our recent works. This is a 3D NACA 4412 aerofoil. So this is a segment of an aircraft wing. So this would be a 3D simulation, but you're looking at it kind of on as a side view. The flow quantity you're looking at here is not actually the flow physics. This is looking at the mesh deformation. So this quantity plotted is the dy d eta grid derivative, the metric derivative. So this is just showing that as we get closer and closer to the simulation, to the surface of the aerofoil and the wake, we are refining the grid smaller and smaller and smaller to be able to resolve the physics that's happening at the aerofoil surface and then also at the wake region. And to be able to do aerofoil simulations, this is a larger view of the picture I showed on the previous slide. To be able to do these kind of 3D DNS of aerofoil simulations, we have to go to multi-block. This is mainly for meshing reasons. You can do an aerofoil with like a single block O grid, but then you have a lot of numerical issues at the trailing edge. So you have a kind of a numerical discontinuity at this point here. And if you try and simulate this with an O grid, you get into a lot of numerical issues. And also it's hard to control the clustering of grid points down into the wake if you're using an O grid. So we use multi-block capability. So this is a recent addition to OpenSBLI. So this is where we split the domain into 3 separate blocks. And then the equations are solved on these 3 blocks separately. And then we have interblock halo exchanges, and this is all provided by the OPS DSL. So we can set up a problem like this, running kind of 3 simulations essentially, and then doing a communication between these blocks. Finally, we have some other collaborations that are using OpenSBLI. I've highlighted a couple of them here. The one on the right is a Mach 6 roughness-induced transitions. This is a hypersonic problem, 6 times the speed of sound. And in this simulation, they are looking at the transition mechanism for a roughness element. So this element here is a 3-dimensional bump. So you could think of this as a kind of an imperfection in a surface of an aircraft surface. This may be like a rivet or something. In this simulation, they add some disturbance upstream, some kind of free stream noise, and then they're looking at how the flow transitions to turbulence behind this roughness element. And this was validated against the ELTE code at ONERA, the French aerospace lab. One of our other users is Gary Coleman at NASA Langley. So Gary's been using our code for about a year and a half now, and I spent some time there earlier this year to do some work with them. So Gary's running turbulent supersonic channel flows. These are quite high resolution cases, up to about 1 billion mesh points, doing very high fidelity simulations of turbulent flows with heat transfer. And this is very useful for them for their turbulence modeling. They can use this to develop models which would then be applied to large scale aerospace applications. And we can also generate very large data sets which can then be used to train machine learning algorithms, for example. So yeah, we have OpenSBLI installed on one of their GPU clusters, and we can run up to kind of 1 billion grid points on as little as 8 to 12 GPUs using our low storage algorithms. So this is a very modest kind of size really to be able to do these scale of simulations. OpenSBLI has also been used as a performance benchmark for Archer and Archer 2, which are the UK national HPC facilities. And a few years ago, I also went to Cray in Bristol, where we were testing the code on the ARM-based GW4 system in Bristol. And we also use OpenSBLI to do some kind of outreach as well. So we use it to teach turbulence to students on the master's course at Southampton, where we give all of the students a Linux virtual machine with OpenSBLI installed on. And then they turn that on the university workstations, and then they can run some DNS of fluid problems. And this is very different from the kind of CFD that they're used to at university, where they're used to using quite commercial products like Fluent, where they've got a nice GUI that they can just point and click on. This gives them some experience in using a research code and handling all of this data. And then we ask them to do some flow visualization and extracting data from the simulations. So to conclude, CFD has significant challenges for numerical codes in terms of the computational cost. But with exascale computers and domain-specific languages, we will be able to run high-fidelity simulations of flows, which at present would be impractical. Domain-specific languages such as OPS give us ease of access to emerging computational architectures such as GPU machines. This is where we are offloading the parallel implementation to people like Isfan and Gihan, who have the specialist knowledge of the architectures and know how to get the best out of them. OpenSBLI itself uses symbolic algebra to generate the OPSC code, and we're able to perform symbolic manipulations and optimizations at that level in terms of how we actually write the code out. And then optimizations in terms of the parallel implementation is handled by the DSL themselves, and we don't need to worry about that. one of the benefits is that we can do low memory intensity compute on the fly algorithms, and you can generate code that would just be completely impractical to write by hand and completely unmaintainable. And then, yeah, finally, I've shown some examples of the research that we've done up until now with OpenSBLI. These are some references. The first reference is the most recent one for describing the code. So if you're interested in the code, that would be the good one to check. In terms of my personal work, I will be doing extensions now to non-ideal gas and non-equilibrium effects. So these will require some more functionality to be developed for OpenSBLI as well. Yeah, thank you for listening.
Thank you, David. Very interesting stuff. Any questions from the audience? I have a bunch. So sort of as a general overview, I think it's today this talk and then the Vito talk and the ExaStencils talk. It's a very interesting to compare these in terms of how things are layered, and Sebastian put this very nicely. That at different layers you want people with different expertise, and here I want to bait Fabio a little bit too. So what do you guys think about layering? So David has the top layer and then doesn't care anything about the bottom layer. Sebastian has 4 layers, but Fabio only really has 1, or rather 1 organization, or so you guys go the full vertical depth, I guess. So Fabio, how much do you need to be an expert in the numerical algorithms to be able to develop the Vito, for example?
So yeah, the user for us, the user with the Vito only sees 1 layer, which is the Python layer with the DSL and SymPy and all those things. He or she doesn't see anything about the compiler. So yeah, if there's a new feature that needs to be developed, you don't. I mean, basically, you'd have to learn how a compiler works to do it in the Vito. What users can do is to edit, is to customize directly the generated code, which, as happens with the OPS and OpenSBLI, I mean, we are generating full programs. Okay, so that is still a viable option. But yeah, the entry point, ideally for us, is just, it's just the Python layer. Yeah, I mean, the compiler itself, as I said in my talk, is stratified. It consists of several layers and intermediate representations. But but for users, it's just 1 entry point.
Yes. So I think you showed that. And so David is just showing the slide with the with how you express so an equation, or rather you already expressed the discretization in some sense. Can you guys talk about different options in how you discretize and what stencils you pick for the same equation?
Yeah, so I think from our perspective, this one example here is showing the equations in one form, but a common approach for fluid dynamics is also to express these derivatives in a skew symmetric formulation, which is where we split the derivatives up into 2 terms. They're analytically equivalent, but numerically they're not at all. It improves the numerical stability a lot if you write them in a skew symmetric formulation. So our users, depending on which test case they're using, they will write these equations in different ways. You also have the freedom to, so this syntax here is d rho dt plus d rho j dxj is equal to 0. But if you've got a source term, like in the transitional cases that I've shown, you want to add a source term to these equations as well. So they have control over that. So yeah, there's a lot of flexibility in terms of how you specify the governing equations. We think the system could also be used for other types of equations, but up until now, we've been limited to compressible Navier-Stokes. But for something like magnetic hydrodynamics would be a good extension to these. This is where you take the same equations for fluids, but then you add an electromagnetic, the equations for electromagnetism, and then you could do simulations of plasma. So that would be one of the extensions that we would like to do in the future. And in terms of different stencils, it's mainly controlled through the different ordering of the scheme here. So switching from a 4th order central to a 10th order central. And then we also have some other ways of, schemes that have kind of filtering or optimized schemes as well that can use different coefficients depending on the different application. If you're doing like an error acoustic kind of simulation, then you would want these dispersion relation preserving schemes, which are optimized for a certain domain. So yeah, there's a lot of options that you can do.
So probably one key difference with us is that, so as far as I understand, you have a number of preset numerical schemes which the users can import and choose from.
Yeah.
Which is cute. While for us, it's a bit lower level because that's entirely up to the users again. So there's like, for example, the finite difference discretization, when you take a derivative, you get, the default coefficients that you normally get with Taylor expansion and stuff like that. But if the user needs to do something more special, there are ways, there are mechanisms through the DSL, but there's nothing preset. There's an API to do that, to use your favorite custom coefficients for your stencil, for example. But you have to use this API. There is nothing pre-existing.
Yeah, we also have a feature called user-defined functions, which just gives them a kind of an empty slate of being able to add their own equations. So they can build up their own, if they want to add something like a nonlinear filtering step at the end of the time loop, or if they want to do like a popular use case for our code is accumulation of statistics, where you may want to compute a whole energy budget where you have lots of different terms of derivatives. Yeah. So we have an interface where users can specify extra components that then get added in at a certain point in the algorithm.
Yeah. And by the way, this is, I mean, conceptually, this is like, it's the same story with boundary conditions. So we don't have any preset boundary conditions, not even Dirichlet. I mean, if anything the users want to do, they do it through equations. I mean, we call them EQ because that's the name that comes from SymPy, but essentially it doesn't need to be an equation in the mathematical sense. You can see it as a statement, and users can use them as, to express statements in classic imperative languages.
Yeah, for us, there's a kind of a mix. We have some boundary conditions like this one, which is an isothermal wall, which makes the assumption that you're solving Navier-Stokes problems, and it would set your velocity components to 0 on the wall, for example, and you'd be setting an energy based on the Navier-Stokes equations. But then we have other ones where, like, we have just a generic Dirichlet boundary condition, where the input would be a list of equations like this, and then the user can specify whatever equation they want to set on that boundary. And that could be either in terms of derivatives or in the flow variables themselves. And another common use case is also time dependent. So we have time dependent boundary conditions. So for example, this simulation I showed here, in this one, we were adding an acoustic source in the free stream as a source term in the governing equations. But another way of doing this, I have some other work which I didn't show here, is where you modify the wall boundary condition to have a forcing strip where there'll be a narrow region in the wall boundary condition, which will have a time dependence, and then you'll have some time dependent mode forcing, and that will give you your transition, that will give you the initial perturbation to the simulation, which can then transition to turbulence.
Yeah, that's cute, yeah. Basically, we would do that through subdomains in the data. But yeah, that's really cute, really, really nice.
Thanks.
So let me add that I guess in some sense OpenSBLI is starting at out at an even higher level of abstraction, but then as a layered system, they spit out OPS code, and then OPS does further transformation, but there is no transfer of higher level information from OpenSBLI to OPS. So there are optimizations that Fabio talked about, which are much easier to do in a system that is completely, well, not completely, but more tightly vertically integrated than this one, where to do similar optimizations, OPS would then need to again understand what's happening.
Yeah, I think there's always a trade-off for a domain-specific language. The more specific if you made it more specific for fluid mechanics, then you reduce the number of users that you could potentially attract to use your system. So there'll be certainly things that that are done in OPS, maybe like there's like an MPI exchange for each kernel, whereas for a fluid dynamics code, we would maybe just do that once at the end of the time loop. So there'll be things like that where we could do differently, but it's not a large performance difference for us. I think one of the concerns maybe going forward with using domain-specific languages would be kind of interoperability with other libraries. So if you wanted to call like an FFT library or something, how that would interface with the data structures within OPS would be one question we had. And also, for example, in situ visualization, could OPS be coupled to kind of in situ visualization packages that we could then use to do plots during runtime?
Yeah. Yes, the coupling thing is an important problem. Although I think recently we have worked quite a lot to enable support for that. So if we find a student who will do that, that could be really interesting to do. Okay, any other questions, anyone? Okay. So with that, we thank David, and indeed we thank everyone who participated, listened in, or actively engaged in discussions. I think this has been a very interesting workshop. It certainly was for me. So thank you to everyone. If there are any follow-on questions, we probably know each other's emails. If you don't, just ping me an email. I'll give you the contacts. All of these have been streamed on YouTube. So if you want to look back at some talks, you can do that. If you would like your talk not to be on YouTube, let me know and I'll take it off. And also, if you can, please do send me your slides and I'll put them online.
Okay. Thank you.
Sure. Thanks a lot,
Thank you, everyone. Have a nice rest of the week. Hopefully sunny weekends.
Thank you very much.
Thank you very much all.
Bye-bye, guys.